Now, living around in this part of the world, I do have some scope recommendation sizes for you to consider. This assumes that you either don't have a scope or you're looking at upgrading in the future. Refractors in the 4 to 6 inch range, Schmidt-Cassegrains and Newtonians in the 6 to 12 inch range, and Maxitoff Cassegrains in the 5 to 8 inch range. I limited the Maxitoffs to the 8 inch range because, first of all, they're very expensive at over 8 inches to get. And the front meniscus lens is very thick, which allows for a much longer cool down time. So that's where I cut off the Maxitoff Cassegrains. It should be mentioned, though, that if we live in a different part of the world, there was somebody mentioning earlier, Robin, that he wants to go to Australia next year or so. Well, there you can use a much larger scope because the planets are higher in the sky. It means, well, that the seeing conditions will be better. So it opens up the door to much larger apertures, which begs the question, why the heck do we live in this part of the world? Oops, I'm sorry, guys. Just bear with me for a sec. What happened here? Ah, there we go. Perfect. Okay, moving on to accessories. Digital SLRs. They're a great option to use to get started with. And the reason being is that a lot of us have a digital SLR at home. They're really good for wide field imaging, for example, the full moon. And that's because their sensor size is larger than your typical planetary video camera. On the con side, they're heavier to use. So if you have a light duty mount, that may task the mount. The other con side is that the frame rates will be less than a dedicated planetary camera. And frame rates are very important for planetary imaging. And they're also not compatible with some of the planetary imaging accessories we use today, which are namely atmospheric dispersion correctors. And I'll talk a bit more about those later on. So as a result of those factors, they really haven't been embraced by amateur planetary imagers for the high resolution planetary work that we do. Next up, we have dedicated planetary cameras. These are definitely the way to go, in my opinion. They're CMOS-based, high-speed and high-sensitivity video cameras. They're high sensitivity in both the IR spectrum and the visual, and which easily makes them the most preferred choice. You can choose by having either a colored or a monochrome camera, but I certainly recommend that everybody starts with a color. The reason being is that if you want to take a colored image with a monochrome camera, you have to invest in color filters. You'd have to take the video sequences in each of those color filters. And so in other words, you also need a filter wheel. And then it involves just a whole lot more post-processing work to get that final image. And frankly, the way that the colored imagers are out today, they're really become a game changer, and they are becoming more advanced all the time. Even a lot of really well-known amateurs use colored video cameras as well. The most popular types are either ZW or QHY. There's a new one on the market. I think it's called Player One. They're all fairly compatible though. But for example, with the ZWO, there's, the ZWO, there's actually two cameras that I would recommend starting off with, would be the the 204 MC or the 462 MC cameras. The 462 is a new generation camera that's extremely good in the IR range, so that's a good one to consider. However, if you're using a Dobsonian without a tracking platform, then you want to look for a camera that has a larger sensor size, which allow the image to track longer before within the sensor field of view, so to speak. So something like a ZW178 would be a good choice to consider. So for a computer's go, well, you can't operate your camera without a computer. That's a mandatory piece of equipment to have. It doesn't have to be a very fast one, but it should have a USB 3 port. Reason being is that all the new generation cameras now have a USB 3 port, and you want to capitalize on that data transfer speed between your camera and your computer. A large hard drive is nice, but it's not necessary, because you'll soon find out that you'll accumulate a lot of video files, and you'll need a separate portable USB 3 hard drive. And moving on to the software, there are These are all free, by the way. Fire capture and sharp cap, those would be used for taking the videos. Astrostacker is used for the image stacking program. Registax is a very powerful program for its wavelet processing, and then followed by WinJupos. The WinJupos is an optional one unless you use a Dobsonian scope, which you'll need to have that field derotation done. WinJupos is not a very intuitive program to use, but I use it all the time. Once you get used to it, you get the hang of it, it's pretty good. And it does things that no other program can do. So it's something worthwhile getting into and investigating. And there's a lot of tutorials online to show you how to use WinJupos. UV IR cut filters are an essential accessory for a colored video camera. And the reason why is that those cameras are extremely sensitive to the IR wavelengths. And if you don't have a blocking filter for a colored camera, what happens is that the IR wavelengths will bleed into the image, and you will have an image that is not color accurate. It'll blend, it'll push to the red side. Then you'll have to post-process that out. So it's just much easier just to use a UV IR cut filter. And they're running only about $40 and upwards. So they're not a very expensive accessory, definitely worth the money to get one. Barlow lenses. Well, they are important tools for every planetary imager because we want to amplify the image scale. By that, we do that by increasing the focal length and the corresponding focal ratio. The Barlow choice that you would look at getting is dependent on your telescope focal length and your camera pixel size. The universal formula for planetary imagers is you take the pixel size of the camera, you multiply that by 5, and that gives you the F ratio, at least the target F ratio to use under good seeing conditions. Now, here's an example. If, like for example, the camera I use for color imaging is a ZW224NC. That has a pixel size of 3.75 microns, and you multiply that by 5, that gives you an F ratio of just under F19. So if you're using an F10 spec Cassegrain, which I'm using, you add a 2x Barlow lens, that gives you an F20 focal length, which puts you right in the ballpark. Consequently, if you're using an F6 Newtonian, you add a 3x Barlow, and that gives you an F18, puts you right in the ballpark again. IR filters. This is the only filter that you may want to consider down the road. The IR filters allow the passage of only IR wavelengths and blocks all other visible wavelengths. So why is this filter really, I'm getting to the point where it's a must-have for living where we do. And the reason is because it has a knack for penetrating through atmospheric turbulence very well. So if the seeing is not very good, using an IR filter will allow you to get a useful image out of the evening's work. There are several different types of filters on the market, and I'm going to give you some examples. Like what I've done is I tried to simplify this process for you folks, and I separated into the size of aperture scopes. In the 610 to 642 nanometer range, this is actually considered to be an R and an IR filter because an R refers to the red side of the spectrum, but it pushes also into the IR. So you actually get the best of both worlds with those types of filters. They're good for telescopes 4 inches and larger. 642 nanometers to 742 would be good for 8-inch and larger apertures. And beyond 742, you are looking into very large apertures for 14 inches and larger. Now, there's a reason for these sizes based on apertures, because to simplify this as much as I can do for you guys, the higher the number of the filter, the more it pushes into the IR wavelengths spectrum. So, but in consequence, the filter becomes more opaque, so it's harder to see through. So in other words, you need to have a fairly large telescope in order to get enough light to get a usable image from a filter, let's say of 810 or so forth. So that's the reason why. However, if you have a telescope that's large, you can choose for any type of IR filter on the market going down. You can go from the 800s right down to the 610. But you can't go the other way around because your aperture is just not big enough to make use of those darker filters. Now, I have a picture here of Jupiter that I took last year with my C11, and I used a 642 IR filter. To me, that 642 is really quite a sweet spot. But have a look at the amount of structure that you can see in the image here. IR filters have a way of just revealing this faint structures in a way that's superior than a colored image can do, at least from my experience. So they have a knack for doing that. You will also notice that all IR images are done in monochrome. And that's just how it works. Like you take the image in color, it's converted to monochrome. And that's how basically how it all works for getting a proper IR shot. There's other filters on the market, for example, like there's a CH4 as a methane filter for imaging Jupiter. There's UV filters for imaging Venus. But those are very specific and something that you can look at getting down the road if you still have an interest in doing planetary imaging. And if cost is a factor, you can consider just using a red filter, and that'll help penetrate some of the atmospheric turbulence as well. Atmospheric dispersion correctors, or ADCs. These are handy little gadgets, and they're for imaging targets that are low to the horizon. And around from these parts, it's always Jupiter and Saturn. So when an object is low to the horizon, I'm sure if you ever experienced this, but when you look telescopically at something object low to the horizon, like Saturn, Jupiter, or whatever, you will notice that there's a color shift with it. And that culprit to do that is atmospheric dispersion. Like have a look at Saturn here, for example. You will notice that we have blue color on the top and we have red on the bottom. So there's a vertical spectrum we were seeing here with Saturn. By the way, this image was defocused just to really accentuate this, this dispersion effect. So how this little gadget works, and it's shown here in the image on the right. It looks kind of like a Barlow lens, and it has two levers on the side of the corrector, and each one of these levers has a prism that's attached to it. So when you move these levers, you're basically overlapping these the prisms over top of each other, and by doing so, you will be able to counteract this atmospheric dispersion and have a more color neutral image. One thing about these atmospheric dispersion correctors is that they're best used with focal ratios of f15 or longer, which means, and that's the reason why it's placed this way in the optical train, because it's always placed after the Barlow lens, because you want to have the image amplified before the insertion of the ADC, so you can make better use of it, and then the camera fits into that. It's really quite a must-have for serious planetary imagers, and it's most beneficial for colored video cameras. I've certainly used it for visual astronomy too, and I really like it for that. Last of the accessories to consider would be focusing devices. Focusers have come a long way from the days when I first had a telescope, and because now, like in the image here, you'll see it has a coarse focus wheel here, and it also has a fine focus wheel here. These are quite nice, but I gotta tell you, every time you touch the focuser to make an adjustment, you will introduce a vibration to the image, and you're gonna have to wait for the image to settle down before you can be assured that you have an accurate focus of it. So for that reason alone, I went ahead myself and I purchased a motorized focuser, and I have absolutely no regrets about using it. Though it doesn't have to be a fancy one. Matter of fact, the one that I own is the one that is imaged here, and this is from Rigel Systems. And it just is a very basic unit. It's nothing fancy with it, and it's just engages with the teeth of that's applied as part of the kit to your focuser, and it allows you to make some very fine adjustments without inducing any vibration. Focusing is a really, really critical thing to do for planetary imaging. If you don't get it right, you've essentially wasted your time with that imaging run. So you have to be patient with it, and it's a worthwhile accessory in my opinion. Putting it all together. This is what my setup looks like with my ASI 224MC colored video camera. So on the image on the right side here, Here, this is my Barlow lens. It's inserted inside the atmospheric dispersion corrector. And here you can see the levers that move those prisms. And here is a series of low profile adapters that allow me to move the camera independent of the atmospheric dispersion corrector, which is a nice thing to be able to do. And because this is colored video camera, what you cannot see is behind here, I have my UV IR cut filter in place. Now, the image on the left is what it looks like when it's inserted inside the telescope. Here, the telescope I'm using for the example is my 8-inch f10 Maxitov Cassegrain. And so here is my electric focuser and the controls for it here. But in this case of this telescope, as well as for all the Schmidt Cassegrains that I know, always have a focus by moving the primary mirror. I prefer not to do that because I don't find it accurate enough for planetary focusing. So what I've done is I have a rack and pinion focuser, this one being a Starlight Instrument Feather Touch, and it is fastened to the visual to the back of the telescope, and then my focus motor is just attached to that focuser. So summary of my recommendations for you. First, start with what you have, and you can always upgrade from there. It's best to start with a colored CMOS video camera. And if you do start with a colored video camera, you will most certainly need a UV IR cut filter for it. Then start with simple targets first and build on your success from there. The moon is a fantastic target. It's always readily available. You can cut your teeth on it really well. And you might have so much fun imaging the moon that you might not want to even look at imaging another planet, because it's a lot of fun, and I certainly enjoy my time doing it. And then from there, you can build your accessories over time. For example, you could add some more IR filters to your arsenal. You can invest in another finder scope that makes it easier to find the planet. And one little accessory that I use that I recommend is actually a reticle eyepiece, because it's really hard to put the planet on a very small chip of those colored video cameras. So by what I do is I insert the reticle eyepiece in the focuser. I get it exactly perfect on the planet. Then I put in my my camera, and then it lines up really well. Oops. So no presentation is complete. Let's have some pretty pictures. And these are images I took last year with my C11 telescope. And the seeing conditions were quite good for these shots. This year should be a great year for planets, specifically Jupiter and Mars. Jupiter will be higher than it was last year, so that'll present some better imaging opportunities for us. And Mars will be in Taurus, which would be nice and high in the sky. So that again will be a good target for us. You just have to bundle up because it'll be closer for us in December. So thank you very much for your time. I can answer some questions if you have any right now, or you can always reach out to me personally after that, and I can share my email with you down. Pardon me, I'm just going to stop sharing here. I can always share my email with you as well, and we could engage with that. Or you can sign up for the mentorship program as a learner, and I'll be happy to give you some one-on-one advice. And I see Darren has his hand up. Darren, yes.
Yeah, hi, Mike. Great presentation, by the way. Thank you very much for this tonight. I had a question for you regarding the IR cut filters, the ones that pass, or basically IR pass filter, actually, is the better way of putting it. Yep. I noticed that you had different values depending on aperture. Most of these cameras peak around, what is it, about 808 or somewhere in that range? 820?
Actually, even further than that, Darren. I think you can get up to 1,000. They're really quite...
Where they peak? You mean like where their peak response is?
Oh, no, in terms of like the nanometer range where they image to?
No, what I'm talking about is if you looked at the actual, like, I guess you could say the quantum efficiency curve, they tend to peak, if I remember correctly, it's somewhere around 800 nanometers, in that range, 800 to 900 for sure. Mid-8, I think, is where they sit. So I was wondering, when you're talking about that rule of thumb you had for aperture, is that based on exposure time and the amount of aperture you have? Because obviously the larger aperture you have, the deeper you go into the near IR, And it seems to me that you'd want to go the other way almost because you'd have more light. I'm just curious.
Well, those filters get to be really. Oh, by the way, Darren, the one camera you're referring to that has that quantum efficiency peak at that range around the 800, it would be the 462 MC, which is probably the next camera I'm going to buy, by the way. And so it's just superb for IR imaging. But again, the IR filters are kind of tricky, and I try to find a way of putting it in a very easy to understand sense, because they're fairly complicated. Because as soon as you get into in pushing further into the IR spectrum with your cameras, you will find out that you will have a loss in resolution with them when the seeing is good. When the seeing is good, actually the visual spectrum will be better for resolution.
Well, resolution is proportional to wavelength, right? So therefore, if you're looking at something like 950 nanometers, that's like double 425. So automatically you have half the resolution at 950. You do it in the blue, say, as an example.
Well, I mean, Darren, from what I read and understand is that there will be there'll be a loss in resolution of the image with those high IR filters, and that's part of the reason for using a larger aperture, because you'll be able to make up for that loss of resolution with the enhanced resolution you can get from
Gotcha. Yeah. So that's why you're recommending the larger aperture to offset the disparity you get with the longer wavelengths, because you're going to get lower resolution with smaller apertures. I got it now. Thank you.
It's part of the equation, Aaron. It's for sure, Darren. It's an interesting thing. And you know what, when I was writing this up, I knew you were going to ask me a question about this. I knew it, Darren.
Well, I'm happy not to disappoint. Thanks.
So, Mike, there was one quick question before we start the meeting in the chat, and it was just a question that was asked: how about using a Mac-Newt?
Mac-Newts are fine. Absolutely. Yeah. Mac-Newts are wonderful. Again, they're an F6, so they're kind of like the same, like a F6 Newtonian. You just have to choose the right Barlow lens for it. But Mac-Newts are wonderful. I've seen some great images taken with Mac-Newts.
Great. Thank you very much. Well, just thank you, Mike, for doing an excellent beginner session tonight on planetary imaging. And with that, we're going to get ready to move into our regular meeting.
Oh, hi. Oh.
And good evening, everyone. Again, for those that just joined us, I'm Dennis Lyons. I'm the president. And is my screen still sharing, or did it just stop sharing?
It's sharing. Oh,
It just stopped.
It's sharing no more.
Showing no more. Look at that. Try this again.
Yeah, that's better. Thanks.
There we go. And again, good evening. So again, thank you to Mike Karakas for the beginner session tonight. And the agenda for tonight's meeting is I'll be doing some welcome, a few announcements, talking about one of our volunteer positions that we're recruiting for. Tonight, What's Up is being presented by Bryan Stach. What's New is Dr. Danielle Pahud. Then, depending on time, we will have a short break. And then our main presentation tonight is Dr. Dale Frail, Astronomy from Antarctica. And then afterwards, of course, our traditional virtual get-together. So just a few announcements here. Just updating everybody for the bylaw reviews. It's expected, Judy has said that she expects to present sometime in August or September to the membership, what the changes will be. Tonight, there won't be any breakout rooms. We're just going to have the one, it'll be on so people can chat in that until we have the break is over. Just a reminder that we are working on a Mars geology field trip this summer. We don't have any details. Probably early next month, we'll contact and make those arrangements and start getting the information out. We are looking for volunteers for meeting presenters for anything during the meetings, as well as the beginner sessions. Reminder, our Loner Scope coordinator is Mike Karakas, and the information to contact him is on the website. We have a binocular interest group. Darren Henning is the one person that is coordinating that, and you can contact him. Future meeting formats to be blended in person and Zoomish. The reason I use Zoomish, there'll be different medias that we're going to use, but we do intend to carry on with Zoom. There's a lot of different technical details we have to figure out once the U of M allows us to go back in person. But we do intend to have a way to have Zoom. And the reason for that is several members have indicated that because of Zoom, they're able to attend the meetings because they live outside of town. And then as well, the opportunity to bring in guest speakers like Dr. Dale Frail tonight from outside Winnipeg and the community here. Public events are coming soon. We are looking at Astronomy Day in April will probably be the first public event that's put on. And we hope to have some more information out in the very near future so people will have an opportunity to volunteer. Just want to mention there, Jay had sent out an email to the membership about women and girls in astronomy. If you hadn't looked at it, I recommend you look at it and to see if there's some ways that you may be able to participate and support that worthwhile endeavor. Glenlee, and with all our snow, I know it's hard to think about it, but in all likelihood, Glenlee, once the snow starts to clear, the flood will probably be a flood risk. And the council will make a decision once we have a better idea of what the flood risk will be and whether or not Glenlee will get closed down and all the equipment removed so that they don't get damaged should there be a flood this year. So the one volunteer position I want to talk about tonight is, these are several of them. These are what's available. So we have a meeting coordinator, a volunteer coordinator, Spring Star party chair, Explore the Universe coordinator, webmaster, mentor coordinator, meeting presenters, finance committee, and observatory committee, primarily volunteers to train new members on the dome and the etiquette for when you're out at the Glenlee, the observatory. All of these really don't take a lot of time, probably on average an hour a week or less, depending on how you accumulate the time. But the one I'll talk about tonight is the meeting coordinator. What the role is going to entails is really confirming that person will confirm the meeting presenters are available, and we have it on a Google Doc where it's all tracked. And just to let you know, we're pretty much have all our speakers to the end of October already scheduled in. So really what it is just confirming that nothing's changed from the time that they confirm their bookings and to when we are looking for the presentation. They recruit speakers as required, but we do seem to have a very active response from the membership of sending us people that could be good speakers. So that really makes the job very simple. When we go back to in-person, they may assist a little bit with meeting IT if required, assisting where they can, if that's in their experience. They will coordinate with our snack providers. Again, you notice I'm talking about hopefully getting back in person. And all that is just to make sure that there is a snack provider set up to have things there for the evening break. They will coordinate and provide the thank you gifts to our main speakers. And again, confirms the meeting place when in person is allowed again, because occasionally the U of M, as some long-term members know, when there's an exam week, we cannot necessarily have the large auditorium and we get moved to a smaller facility. So those are the roles. And as you can see, it's not a lot to use up, a couple hours a month, actually, not counting the meeting time. So if you're interested, please contact any one of us on the council or myself using the president's email, which is available on the website. And we'll go from there. I just see somebody's got something in chat. I'll just check to see what it is. Michelle Boyce is just letting us know that the snow has been cleared, so you can actually get out to Glenlee. So the snow's been cleared just in time for more snow to come tomorrow, if the forecast is correct. So with that, there is no members observing night scheduled for tomorrow night. So just so everyone knows that there won't be a formal program out at Glenlee tomorrow night. And with that, I am now going to introduce our next speaker for What's Up, and that's Bryan Stach. Please welcome Bryan Stach, and I'll stop sharing so he can.
Great, thank you, Dennis. Okay, so Let me get my presentation going. All right, let's start up with today, or we'll start up with what's up for March 2022, and let's see what's for the night sky. All right, I'm on a new computer, so hopefully this is going to work. I'm going to try something new on this Surface Pro that I have. Okay, we start off with planets, starting off with Mercury. Unfortunately, I'll just be brief here. Mercury and Jupiter is going to be a little too close to the sun to do any kind of observing, especially during the day. The other planets, Venus, Mars, and Saturn, well, they're basically going to be observable early in the morning, and I'll show you exactly what we mean, but we have some big conjunctions happening at the end of the month, and I just discovered something at the beginning of April, what's going to happen. Some of these planets are going to line up in the sky. As for Uranus, it's closing rapidly, so it is only going to be an early viewing. All right. So what's up for March? Okay, of course, we have the daylight saving time happening this weekend. Of course, full moon's on March 18th. We do have the March equinox starting March 20th. I'll explain a little bit of that later. We still have the zodiacal lights visible starting May the 20th for the next 2 weeks, and this will be your last time to see it. The next time you won't be able to see it until fall in September roughly, but it will be in the early morning. Last quarter of the moon will be March 28th. As I mentioned before, we have Mars, Venus, and Saturn in conjunction with the crescent moon on March the 28th. All right, so we'll explain a little bit more about what I mean about the early planets. So you can see here, looking towards southeast, you can see the sun's coming up here. We have Venus, Mars, and Saturn. They'll be visible just before sunrise. Unfortunately, that's the best we can do. Venus would be 7 degrees north of Mars. Later on in the month, March the 28th, as you can see here, we do have Venus, Mars, and Saturn very close to the crescent moon. Again, almost in the same position, hasn't moved much. But Saturn will start to move up and overtake Mars eventually. So that'll be interesting to see. I'll explain more about that later. Next slide. Okay, if you do get up a little earlier on March the 28th, you'll still have some darkness to observe these planets. Now, as I mentioned in the beginning of April, this is what's going to happen. And I'm going to see if this is actually going to work. You can see Saturn is going to eventually overtake Mars, and that's later on in April. All right, so what's happening with the Milky Way? The Milky Way is going to be overhead starting tonight. As you can see here, we have the constellation Orion due south. And of course, it's going to be an early evening event. We do have the Milky Way. And do I have Andromeda Galaxy? So just take a note here, because we have the Milky Way here. So just bear in mind where Andromeda Galaxy is, because we're only seeing part of the Milky Way. Now, without the constellations, this is what the Milky Way is going to look like. Again, we have Orion constellation here, and we have Andromeda Galaxy, or M31 showing there. Okay, so later on in the morning, the center of the galaxy is going to start to rise, but still it's going to be low in the sky. Again, as you can see here, we have M31. I hope you guys can see that. And okay, again, this is later in the morning. This is just before sunrise with still some darkness. Again, we still have the Milky Way, and then we're approaching on the center of the galaxy. Again, I want to mention about that's M31. So the next slide here, again, this is just showing that we're creeping up on the center of the Milky Way, the galactic center to be exact. And this is the one screen I want to show you. This is the entirety of the Milky Way. And as I mentioned before, this is a little galaxy right there, and that's M31, and that's the Andromeda Galaxy. Just kind of gives you an idea of what we're seeing in terms of the Milky Way. Next slide. Okay, I'll just explain briefly about the zodiacal lights. Of course, it's going to be just within a half hour of the evening twilight, looking east. Of course, this is your last chance to see it. Starting March the 20th, next time, as I mentioned, it won't be until the fall. but the moon is not going to interfere with it because it will rise pretty late in the evening. All right, so here's my picture of the zodiacal lights. I just want to mention one thing I want to point out. This is the sun path. Looking east, this is the path of the sun. Just kind of giving you an idea how it looks. All right, next slide. We'll talk a little bit about the March equinox. Unfortunately, it won't mean equal days and nights, but it's starting on March the 20th at 10:33 a.m. local time here in Winnipeg. All right, now the forecast. What do we have for the forecast? Unfortunately, it doesn't look promising. In this screen here, we have humidity is going to really jump up to 100% starting next week, but the temperature, it looks like it's going to rise a little bit above 1 degree starting Tuesday of next week, but it will drop down later. It'll get cold again around minus 10 degrees next Sunday, but in terms of clouds, as you can see here, we are expecting some snow tomorrow, and we are expecting a little bit of snow on Thursday. But if you're going to do any observing, according to this forecast here, this is probably the only time that we get to see some clear nights, and that's next Saturday night. All right, just before I go, all right, daylight saving times. I guess you guys are know about this weekend. We turn our clocks 1 hour ahead, but for most of us, we have cell phones and computers, so that's pretty much done automatically, so you don't have to worry about it. But apparently, Canada has observed daylight saving times for 110 years, starting at 1908. So that's pretty impressive for a long time. So I don't know about how you guys feel about the snow, but I think we all can relate to that. Okay, thank you, Dennis, and that's what's up for March.
Thank you very much, Brian. So our next speaker is Dr. Danielle Pahud. Danielle, are you here? I know you might be using one of the other pseudonyms there, so. I'll ask again. Danielle, are you in here tonight? All right. Well, there we go.
We're running ahead of time. Sorry, we're ahead of where we should be according to the agenda. So maybe she's not ready. I don't know.
Right.
Yeah.
Okay. So what we'll do is Ed will we'll allow everybody to unmicrophone for now, and if Danielle shows up, oh, I just saw some people show up here, so I don't know if she's on there. Danielle, are you here? Okay, so maybe if you want to unmute, and then I will check with. We'll have an open session for about 15 minutes, and if she comes in, then we'll shut the session down, and then she can give a presentation. Okay, Ed?
Yep, sounds good. Thanks.
All right, so everybody should have the ability. I think everybody's got the ability to unmute. So we're going to have a 15-minute social, just to chat a little bit, or for whatever we want. And if Danielle shows up, we'll put that on. And I'm going to go off just for a minute while I chat with our evening's presenters, just to make sure he's okay starting early if that's the case. And yeah, so welcome everybody. And this is your opportunity to just chat and see how things, how everybody's doing and what they plan to do here in the near future.
Well, somebody's going to have to break the ice here.
Okay. Hi, everyone. How are you doing?
Hey, Mark.
Mm-hmm.
I was going to say, notice Darren has his hand up.
Hello.
Mm-hmm. Hi, Karen.
Were you guys able to see my markings when I was marking the M31
Yes,
kind of thing?
absolutely.
Yeah, that worked really well. Yeah,
it worked really well.
You know, I got the Surface Pro 7 here. So I got the Starless pen. So I just love this new computer. What a difference it makes in the camera, the quality, everything. It's just, oh, it's just great. So that's it. Thanks.
You know, Brian, I have the same one. I have the same one from work, and I'm using it.
Oh, you got the same Surface Pro?
Yeah, that's what I'm. Well, it's not the Surface Pro. I don't think it's Surface Pro. So it's not as fancy as yours.
Aaron, you're rustling.
Oh dear.
Okay.
Yeah, I'm trying to pull it.
Put mute on.
There. There we go.
Yeah, I noticed like now I can do this, which I really like. Oops, I'm gonna go here, here.
Okay.
Now I can do video settings. Just for low light, service camera. Oh, wait. Oh, background filters. Okay, blur. There we go. Now I can do the blur like you.
Blurred.
Right. You can only see my face, can't see the background, just like Mark. Now I'm gonna try some background pictures later. But I really like
when the
this
party really starts.
Yeah.
I want to turn the volume down just
Mike, that was a really interesting talk. I felt like I was learning something instead of just watching slides.
Oh,
That's getting involved.
So Brian, you miss
Yeah.
going down south to Arizona and the zodiacal light this time of year?
Yeah. Oh yeah, that was the time. Yeah, that was the time that we were at Arizona. Yes.
Quite often. So yeah, it was a regular feature for us.
Yes, and if you see that little red light at the corner of it, that's Jay at his computer. Yeah, that was good times. I really enjoyed it. At the first, I couldn't, when you guys parked off to the side and he goes, yeah, there's the zodiacal lights. I'm looking. I can't see it. But when you look at it and finally realize where it is and how big it is, yeah, it's bigger than you think. But when we got back to Arizona, I started taking pictures of it. So it's great.
And the
We're
dark
back to
skies.
our house. Sorry?
And the need for the dark skies, how well it stands out in those.
Yes, we got some really dark skies. Yes.
I just noticed that I think Dr. Pahud is here.
Hi.
Hi. Good evening.
Am I late?
No, actually, we were running early. So
Okay.
no, we go to great pains to put an agenda in, and then of course it never works.
Okay, sorry. I tried to give myself enough of a buffer. I'm actually in Edmonton visiting family, so
I see.
if there's background noise, it's my niece. So I'm sorry to keep you all waiting.
Oh
Hold
yeah,
on.
no, not your fault. No
We
problem.
just went to let everybody have a chance to chat. So I'll ask everybody who's got to just mute your mics again, please. And then again, I will introduce Dr. Danielle Pahud, and she's going to do What's Up tonight.
Oh, what's new?
No,
What's new?
What's
Oh
new?
gosh, I was gonna put together the wrong presentation.
No, you did not.
Okay.
You have the right presentation. I have the wrong words.
Okay. Well, thank you so much for having me, everyone. It's really nice to be here and presenting to you. I'm going to start by, it says host disabled participant screen sharing. So if it's possible, I'd love to share my screen. Okay, perfect.
Sorry, that was me.
No, all good. Okay, here we go. What are people seeing? It should be a Chrome presentation. Is that what people can see?
Yeah, no, I can see it.
Perfect. Thank you so much. Okay, great. Oh, I see Jim is here. Hi, Jim. Jim Birch. Nice to see you. Okay. All right.
Hi. Hi.
We'll chat after. Okay, Jim? Nice to see you.
Thanks. It's good to see you.
Okay. So I did a bunch of reading, as I usually do, for what's new, which is always nice to keep me kind of up to date with other fields in astronomy. And so two of the stories that I found were really interesting was an update from the HOPE probe at Mars, which is a mission that's really international, but is kind of originated out of the United Arab Emirates. And so I really like thinking about international space effort. And the second topic I'll be talking about is that the largest molecule yet has been found in a planet-forming disk. Darren, I see that your hand is up. I just got a little alert. Did you raise it again? Okay, I'm going to proceed, but if you have a question, please don't hesitate.
Sorry, Danielle, I'll put it down. Sorry, my apologies.
No, it's all good. Sorry, this is my teaching instinct. As soon as I see a hand up, I impulsively want to ask. Okay, so the first story is updates from the HOPE probe. And so the HOPE probe is, oh, this is not fitting on my screen. Let me just, good. Oh boy, here we go. It's a mission out of the United Emirates. And its primary mission is to provide the first continuous global analysis of the Martian atmosphere, daily surface changes, and seasonal variability over the course of a Martian year. And so it does this by having quite an elliptical and wide orbit with an inclination. And so it orbits pretty rapidly. And so it can kind of see the full disk of Mars during most of its orbit. And so it has 3 scientific objectives. The first is to characterize the state of the Martian lower atmosphere on global scales and its geographic, diurnal, and seasonal variability. The second is to correlate rates of thermal and photochemical atmospheric escape with conditions in the collisional Martian atmosphere. And C is third, to characterize the spatial structure and variability of key constituents in the Martian atmosphere. So these are scientific mouthfuls to say that we're trying to figure out what's going on in the Martian atmosphere, varying globally from day to day and from year to year. So this mission was launched July 20th, 2020. It inserted into its orbit about a year ago, and so it's just completed its first full year in orbit. And this is a little diagram of its orbit. So it's orbiting quite far out from Mars. And this is an image of the spacecraft and some of the UAE team working at LASP in Colorado. And so the first science results were presented at the 53rd Lunar and Planetary Science Conference, which happened this week from Monday to Friday. So today's the last day of the conference, and I poached them nice and fresh. And so the team has been working furiously, I'm sure, to come up with science results. And so I'll kind of go over them quickly today. All right, so HOPE has 3 main instruments. They're all imagers. So EMIRS is the first one, which stands for Emirates Mars Infrared Spectrometer. And so this is this column of graphs, this white and blue column of graphs. And so the spectrometer measures dust, ice, and water quantities along with atmospheric and surface temperatures. And so the colors shown here in white is less water and fewer ice clouds. And in blue is more water ice clouds. So we're looking at kind of water ice, cold water clouds on the surface of Mars. The second instrument, XE, is the Emirates Exploration Imager. So we're making liberal use of which letters to capitalize in making of acronyms, which is a hobby in astronomy. But this is a dual telescope imaging system that views the full disk, and it images in 6 different band passes, all in the optical. And depending on where the spacecraft is in its orbit, it has a single pixel will have a resolution of 2 to 4 kilometers. And so these in the middle column are pictures from XE. And so in white, we see clouds, and then in black, it's either nighttime or just fewer clouds. And so you can see here that the white visible clouds correspond quite well to kind of darker water ice areas. And then the third instrument is EMUS, or Emirates Ultraviolet Spectrometer. And this is a far ultraviolet imaging spectrograph, and it observes kind of 2 broad regions geographically in the atmosphere. So the thermosphere, which is between 100 and 200 kilometers of altitude off of the Martian surface. And so the thermosphere here is particles are still colliding and are still in thermal equilibrium. But observing this area allows us to observe UV day glow emissions. So light coming off of particles that are combining and recombining due to sunlight. And so the UV day glow emissions come from hydrogen, oxygen, and carbon monoxide. And then the second band or region is the exosphere, which is above 200 kilometers in altitude. And exosphere just means a very thin atmosphere. And it's in this region that particles are able to escape. And so this observes bound and escaping hydrogen and oxygen, studying gas escape from the tenuous atmosphere. And so again, this is morning, kind of noon, where the full disk is illuminated, and then night. And so over the course of this year, they've tracked dust clouds and dust storms. And so here, they've also published a Mars Atlas, which is really cool. It's a Google Drive, and this is where both of these charts came from. So they've made a really nice compilation of images. And so here we have the XE image of Mars, and then here we have the EMIRS kind of spectroscopic image, where in orange we're showing dust opacity, so how thick the dust is. And so they're, the left-hand image is on December 9th, 2021, and they are tracking a dust storm. And so the green asterisk is just to help you kind of locate similar locations on the disk, given Mars's rotation and the orbit. But you can see that this dust storm region here corresponds to high dust opacity here. And then a little over a week later, you can see there are more clouds kind of moving up towards the equator, and the dust is shifted. You can see that this is also represented in the dust opacity. One of the really exciting discoveries is that because it can see the whole disk at the same time, it's really able to see aurora on Mars. And so we know that there have been observations of aurora on Mars before. So NASA's Mars Express and MAVEN orbiters have caught glimpses of aurora on Mars, but because they were so much closer, they just kind of got snippets as they orbited, because their field of view was much smaller. But HOPE's global view enables it to see aurora far more often. And so one of the things that's different about Mars than Earth is Mars does not have a global magnetic field. There are just kind of crustal remnants of magnetic field that are patchy and closed in some regions and patchy and open in other regions. And so when we're studying aurora on Mars, it's also studying, or it tends to correspond with where the magnetic field, the remnant magnetic field, interacts with the solar wind. And so there are three different kinds. I'm a sucker for aurora. I'm sorry, I'm going to spend a little more time on this. There are three different kinds of aurora on Mars. So there's diffuse aurora, which is generated when the atmosphere interacts with charged particles flooding in from solar outbursts. And so that's that. Proton aurora, which is only detected on the day side. And this comes from the protons in the solar wind that kind of rain down directly onto the atmosphere, the hydrogen in the atmosphere. And then discrete aurora are an ultraviolet phenomenon triggered by electrons ramming into Mars's upper atmosphere. And so these observations of the discrete aurora were rare in previous data, but HOPE has already detected a number of them. And it has detected discrete aurora in about 2/3 of its observations, which really changes our ideas about how prevalent discrete aurora are. They've also discovered that discrete aurora are more common at dusk than at dawn. They can have a large, different types of morphologies. So they can be large and sinuous. And so this probably corresponds with magnetic field, but the dusk-dawn asymmetry has yet to be explained. And then here, this is an image again from that Mars Atlas. So these are two different observations of aurora and discrete aurora occurring in far ultraviolet. So there are wavelengths here. The green scale is in Rayleighs, so black is not much emission. White is a lot of emission. This is the sunlit part of the disk. In teal and purple, are magnetic field strength outlines or contours in both negative and positive polarity. And so you can see that the aurora falls within these kind of blobs of strong magnetic field. And so on the left-hand side, the discrete aurora follow the remnant magnetic field really well. And then just because nature likes to serve us counterexamples, on the right-hand side, the aurora is not super correlated with where there are crustal magnetic fields, but the aurora was driven by an interplanet, like a coronal mass injection, an interplanetary coronal mass injection. So really active space weather can drive different types of aurora. Okay, so what's next for this exciting mission? So the science team has given us the teasers for this upcoming data release. And so the full data release will be April 22, so just next month. And they're hoping for a possible start of an extended mission. So they're coming in to the end of their primary mission phase, and we're hoping to, I have nothing to do with this mission. They are hoping to extend the mission. And so there are several different timescales of interest for future HOPE studies. And so hopefully looking at the day-to-day variations, or variation over the course of the day, variations over the course of the season, and then from year to year. So is one perihelion the same as the next? Is one summer the same as the next? And then starting to characterize the daily cycle. Great, and so as HOPE science results continue to roll in, they'll complement results from two missions that are on the ground. So Perseverance from NASA and China's Tianwen-1 mission. Yeah, Darren, go ahead.
Thanks, Danielle. Great presentation so far. Sorry to interrupt. It's kind of interesting about the aurora that HOPE found. I was, many years ago, I was in communication with a guy from NASA. They were doing contingency planning for a Mars mission and the ability for astronauts to communicate via shortwave, basically, or HF, on the event that, let's say, a dedicated satellite failed due to, say, some unforeseen solar flare or something, and it knocked it out, that kind of thing. And I'm sure, do you know, and I know you're just reporting this and you may not have a lot of data on this, but do you know if there's any future experiments for, let's say, two small probes to land on opposite sides of the planet to do sort of an electron flux density mapping to kind of properly characterize the aurora, or is that part of this HOPE's mission down the road? The reason I ask is because obviously once we get astronauts on the surface, that'll be important for them to be able to communicate. And obviously VHF is only line of sight, right? So just curious.
I don't know if such a mission is planned. I don't think that is part of the instrument suite on HOPE. So far I've only seen these three kind of imaging instruments discussed. Electron density content as a function of height tends to be done with kind of, shoot, I had it and then I had the word and then it escaped.
Well, when you look at the exosphere, like you have, I mean, obviously when you get, the fact that we get aurora at all on Mars suggests there's a very weak magnetic field. There's still an ionosphere, right? But the only reason I mention this is because I'm an amateur radio operator too. So that does kind of come into play here on Earth and we take it for granted. But I'm just kind of curious if down the road, NASA's looking at doing some additional, either NASA or ESA or anybody, doing some additional mapping, because some of that ground-based data can actually help supplement the orbital data, right? For mapping the ionosphere when you're looking at the electron density in the exosphere.
Yeah, so I think the word I was looking for is like it's not quite stellar occultation, but essentially if you look at
you mean like an eclipse?
Kind of. So what you can do with to measure so this is done with Mars. So certain orbiters will look at stars that are just on the limb of Mars, and so then as the spacecraft orbits, it will measure, I think, the Faraday rotation, or like the phase rotation and polarization of the wavelengths. And so, and that measure, that rotation, depends on the electron content. And so you can get electron content as a function of altitude. It's of course line of sight integrated through the atmosphere. So there's like that level of ambiguity. But by measuring stars at a distance from an orbiter, you can get electron content as a function of height. The tricky thing with that, though, is that, you know, stars are only a very fine line of sight. And so with patchy magnetic field lines, that's going to affect your atmosphere differently. And so you don't really have the resolution to talk about the global total like electron content, or really that like a fine scale.
Well, you need a lot of stations to get that level of data, right? Like here on Earth, we've got countless ones, right? But on Mars, we don't have that luxury, right? So, okay,
yeah.
Thanks.
Yeah. Great, thanks. Great question. Yeah, so I think this is really exciting, and these are really great images of Mars. So in my resources slides, I'll maybe post it in the link, but the Mars Atlas is really nice. Okay, and then my next topic, speaking of planets, is the largest molecule found in a protoplanetary disk. And so astronomers have found large, complex organic molecules in molecular clouds, or like cold, dense clouds of gas and dust. But these same molecules are really difficult to observe in protoplanetary disks, mostly because the disks tend to be cold and the gases tend to be frozen onto dust grains into like ice chunks. And that's not how because we can only observe the light that arrives at us, frozen ice chunks don't chemically interact with light the way that we like. Yeah. And so we have to look for protoplanetary disks that are fairly warm, which means that they're still quite young, in order to look for these complex organic molecules in their gaseous state. And so these observations, some astronomers undertook these observations specifically. And so they looked at the star OPH-IRS, and it's in the constellation of Ophiuchus, and it's this one circled in red just below the ecliptic. And it's 440 light years away. And it's a very well observed protoplanetary disk because it has a frequently observed asymmetry. And so typically the gas fills the entire protoplanetary disk. And normally the dust is also pretty well distributed, but in this protoplanetary disk, the dust only fills a crescent shape. And they call this crescent shape a dust trap. And then because most of the dust is kind of concentrated there, it's going to be colliding with itself and with each other more frequently. And so this encourages the formation of complex molecules. And so the detection of a complex organic molecule in the disk around an infant star suggests prebiotic chemistry starts in the space between stars, and then kind of gets pulled into the protoplanetary disk. Okay, I'm sorry for the formatting of this slide. And so astronomers have been detecting molecules around and between stars since the 1930s. And since then, over 200 molecules have been discovered in interstellar space, with recent discoveries becoming more and more complex. But it remains unclear if and how complex molecules migrate from the space between stars into planet-forming regions, and ultimately onto planets themselves. And so the end goal here is, how do we take a complex, maybe organic molecule and eventually build it up into something that's like definitely organic and could form life? And so are these molecules made in space, or are they made on a planet? And so this is essentially what this study is trying to get at. And so, so these molecules need to be in gas form to absorb light for spectroscopic measurements. In most planet-forming disks, the molecules exist as ices, which makes detection difficult. And so Nishanti Brunken from the Lyons Observatory and colleagues just earlier this week reported the first detection of dimethyl ether. So my chemistry is not that good, but CH3OCH3 in a protoplanetary disk, which is one of the most complex molecules found in a planet-forming environment to date. And they've also reported a tentative detection of methyl formate. Yeah.
Sorry, Danielle. Really sorry to interrupt, but this is really neat because when I took my cosmology, this 5 years ago, I was with Dr. Christopher O'Day in Astrophysics 1830, and he talked about possible life in the universe. He talked about molecular clouds. Mm-hmm. I remember reading somewhere some astronomy text or magazine, something quite a while ago, I think it was in the 80s, something about molecular clouds.
Yeah, so molecular clouds are they're really cold, dense clouds of gas and dust, and they do tend to have molecules in them because they're cold enough for molecules to exist. So carbon monoxide is a really prevalent. Methane is also really prevalent. And so there are complex molecules in those clouds, as well as some of these. We've also detected sugars and things.
Are they maybe through gravitational force moved between star systems?
Well, what we think, so molecular clouds tend to be the location where stars form. So they tend to be really dense, and so they kind of self-gravitate and like keep compressing. And then within the clouds, there will be clumps and cores, and the clumps and cores are like extra dense. So if you think of the cloud as like cottage cheese, then the clumps and cores are like the actual cheese bit, and that is going to like contract more and start becoming a star in a protoplanetary disk. And so it's not surprising, that those molecules would end up in the star forming region itself. But as things heat up and or cool down, do they survive and do they make it onto planets? Yeah.
Question, Danielle.
Yeah, Darren, go ahead.
I'll just wait till Jim's done there and then I'll ask mine.
Okay, Jim, go ahead.
Thanks, Danielle.
You're welcome.
Okay,
Darren.
I guess he didn't have any more comments. Just out of curiosity, this particular star system, how old do they think it is, or have they estimated its age?
They have. I don't remember it off the top of my head, but I still have the article open. So I want to say it's less than like 1.5 million years.
So I guess this study now is just going to open the door for looking at different ages of star systems and star forming regions and looking how, I guess, quote unquote, complex these molecules will be. I'm a chemist by, I guess, training. So looking at these, I always find when astronomers look at these molecules and they go, oh, there's, potentially a, phosgene in Venus, and it could be a biomarker, and then they get all excited, or they see something like dimethyl ether or dimethyl formate. And it's kind of funny because these are very simple. I mean, they're building blocks to biomolecules, but certainly not what I would consider complex. But compared to, say, what we see in some comets and so on, I guess they are. Refresh my memory, but are some of these, like at least methyl formate, I remember it's either methyl formate or another variant of that might be present in cometary dust, cometary tails, like the ones that we see here in our solar system. Just maybe refresh my memory on that, because if that's the case, it's very possible that some of these stars are just in the process of forming these kind of things. The other thing I was going to ask is, where, like on these new stars that form, these young ones, aren't they a little higher in the UV spectrum when they first ignite, and then they kind of settle down depending on their mass and so on?
Yeah,
is that not true?
it might depend on their mass, but probably, I think they probably start pretty high in the UV, which to some extent helps us here, because if we think most of the gases are frozen, then having like a really energetic photons can help sublimate.
Absolutely, yeah. They would actually create a lot of photochemistry that then would settle in later. But it's still a good start. This is very exciting stuff.
Yeah, and so what they think is happening in the system, this Ophiuchus 48 system, is that the molecules are frozen, and then it's the young star that is actually sublimating the gases, leaving like a particular area, which I'm about to show, with some of these molecules in gas form, which allows them to detect it spectroscopically with ALMA. But as a non-chemist, yeah, I mean, this is like H's in 2 different places, so it's pretty complex. Although I appreciate that this is nothing. Yeah.
No, compared to biological life that we see here, I mean, the chemistry is much more involved, but still, when you're talking gas phase and tenuous, really near elemental type clouds, and then to have this level of organization is really quite interesting. It'll be very neat to see where this goes moving forward, because I think they're going to find a lot more organic precursors that will be very indicative of potential of, you know, life forming molecules. It should be pretty fun. Anyway, I'll let you get back to it. Sorry to interrupt.
No, it's delightful to have a conversation about it. Yeah, if I had to guess, people are going to look for more complex molecules, and they're going to look for abundances of different molecules at different stages of protoplanetary disks. And I think looking at our own comets, as you mentioned, Darren, is going to be really important and insightful. So this is an artist's conception of the actual disk. This is an ALMA image. So ALMA is a large telescope in Chile. And so this is kind of, they think there's a cashew-shaped dust trap in here. And so in this dust trap, dust grains of a few millimeters collide into larger objects, making up rocks, then boulders, and eventually potentially comets and asteroids, and eventually possibly planets. And so this blue shape from this inset is kind of located here, and it shows emissions from the complex organic molecule dimethyl ether detected by ALMA. And so the emission clearly is not evenly distributed around the star, but corresponds to the dust trap. And this inset is just an artist's depiction of the molecule. And so here, these are 4 different images of IRS 48. In purple, we have carbon monoxide. And so we can see that this gas is pretty well distributed around the whole disk, with maybe a little bit of a dip here corresponding to where the dust is. We have formaldehyde in orange, dimethyl ether, methanol in green, and dimethyl ether in blue. And so the complex molecules are all kind of concentrated on the southern lobe of the disk, whereas carbon monoxide is more evenly spread out. Oh, this is a little video of the dust trap. I just thought this animation was cool. So we can see maybe larger bodies forming. We can see the protoplanetary disk spinning and orbiting the brand new star. We're going to zoom in, and we're going to see a region of overdensity in the gas and dust, and we're going to see particles and dust grains flowing in. We're going to zoom in, and we're going to see collisions and rocks starting to build up and glue together. They're going to be frost covered and stick to each other and slowly get larger. We zoom in even more, and we see particles spinning and changing the way that they spin, and it's this actual change in rotation rates that's going to emit the signal that ALMA is picking up. And so just for context, so the particle, the dimethyl ether, has been found in interstellar space. And it's actually been found at the same abundance ratio as interstellar space. And so there isn't a higher concentration of dimethyl ether in the protoplanetary disk than there is elsewhere. So this supports the idea that the complex organic molecules are created in the molecular clouds that Jim mentioned, and then are pulled into protoplanetary disks by kind of the self-gravitation, and then forming planet systems. Okay, these are my sources. This is the Mars Atlas I was talking about, and that is the end of my presentation. I'll take more questions if there are any, and I will pull up that paper with the age of the age of the system.
So if you have any questions, you can either ask them on the chat if you're shy, or
Oh, hi.
Hi, Jim.
Oh, hi, Danielle. So how's Perseverance doing on Mars?
I don't really know. I assume it's doing well, but I'm not sure. I should have, had I had more time, I would have done a more thorough search.
Okay, I'll just have to keep reading more Astronomy magazine, but I just hope that little helicopter, the dust storm, didn't get it.
Yeah. Yeah, I hope so.
Well, but boy, your Hope probe, boy, that's pretty, wow. That's, well, I guess this is groundwork for when we send manned missions or to, you know, a lot of it is to get ready for a landing.
Yeah, I think there's still a lot to learn about. Yeah, I think there's still a lot to learn. And Michelle wants to make sure that you send some love to that Chinese lander also.
Well, I don't want to keep you, but I was just wondering about the dust storms. Well, in The Martian, I read something about, it wasn't really accurate because you wouldn't have some, you know, people blown over by the wind. I thought the air was like practically, well, very thin.
Are you talking about like the density of dust?
Well, like in the movie The Martian, the demon got blown over by a dust storm. Well,
right.
I read somebody said they took liberties with the science.
You know, I don't actually know what the wind speeds are. The atmosphere is less dense than ours. I would have to look into that and get back to you, Jim.
Thanks.
Yeah, thanks.
I know from one fellow wrote about it, he said, well, planetary scientists say, well, there's not enough air density to really create much of a, you know, destructive winds. But
yeah, okay, Michelle types in the chat that it's 1% of Earth's atmospheric density, so pretty
pretty thin.
There.
Well, thanks, Danielle.
Thanks, James.
Hope your class are going great.
Yeah, they are. Thanks.
Okay, talk to you later.
Yeah, bye. Any other questions?
Looks like, yeah, just some comments about nice talk. Okay, Danielle, do you have anything else you'd like to add tonight?
No, thanks. I will. I'll find that. I'm gonna run after this, so I'm sorry that I have to leave. But I'll find that the link. I'll send the link to the atlas in the chat, and I will find the age of that system and put it in the chat.
Excellent. Well, on behalf of the center, thank you very much, Dr. Danielle Pahud, for doing what's new for us tonight and filling us in on the HOPE mission and the other things that are going on. I hope you have a very wonderful evening in Edmonton.
Thank you.
You're welcome. So I think we're close enough that we'll now get set up for this evening's next presenter. So I'm just giving you a minute there. quick heads up there, Dr. Frail, and then I'll do your introduction. So if I don't see, I think you're probably okay to go still. Just double check.
Is that you?
Yeah, there you go. So if you're good,
I'll
Dr. Frail, I'll give you your introduction, and then you'll be able to share screen and do your presentation if that's okay.
Okay.
All right. So this evening's main speaker is Dr. Dale A. Frail, who was born in New Brunswick, went to Acadia University as a physics undergrad, and got his PhD in astrophysics at the University of Toronto. In 1990, he moved to the National Radio Astronomy Observatory, the NRAO, as a postdoc and has been there ever since. His research is focused on the death of stars and the birth of black holes and neutron stars. He has published over 275 peer-reviewed research articles, including the co-discovery of the first extrasolar planets, the first detection of radio afterglows from gamma ray bursts, just to name a few. More recently, he has led efforts to search for the electromagnetic counterparts of LIGO, Virgo gravity waves, and is trying hard to find pulsars around the black hole at the center of our galaxy, clocks around the rock. Tonight's talk is Astronomy in Antarctica. Please welcome Dr. Dale Frail.
All right, thank you for that nice introduction. You're not going to see me on video tonight because I had to do a last-minute scramble and run home because my internet at work suddenly died on me. So I'm not on the video tonight. But can you see my slides?
Yes,
yes, yes, that looks good.
Great, great. Okay, well, yes, again, thanks for the introduction. I'm really pleased to get a chance to talk to you guys tonight. I wish I could be in Winnipeg in person. I have a lot of friends in Winnipeg. In fact, one of my closest friends is calling in tonight to listen to the talk. So I wish I could be there in person. The only thing that I would add to the introduction is that I have fairly deep roots in the RASC myself. My interest in stars got reignited when I went to Nova Scotia when my parents moved back, left the military. And so I joined the Halifax chapter of the RASC. And then when I was a student at Acadia University, my professor was Roy Bishop, who was a long-standing member of RASC, and many of you will know was also a long-standing editor of the Observer's Handbook. So, as I said, long connections to the RASC. Now, I'm not going to be talking about my own research today. I'm going to be talking about a talk that I prepared for a cruise ship adventure to the Antarctic, where I thought people would be interested in hearing a little bit about the science. And this was motivated by Jay and Judy. Here they are here on the boat, celebrating a successful eclipse. But my research is mostly, as it was introduced, is I'm really interested in radio astronomy, and I'm interested in the endpoints of evolution of stars. So I'm interested in the birth of black holes, the death of massive stars. And these are my toys. Let me see if you can see my laser pointer. I use the Jansky Very Large Array, the VLBA, sometimes ALMA, which the last speaker mentioned, and a telescope in West Virginia called Green Bank Telescope. I work as a scientist at the NRAO, and until a little while ago, I was the director of the Very Large Array. Some of you may know the Very Large Array from the movie Contact from, 1985. I would have been Ellie Arroway's evil boss in this model. And so I was the director of that telescope and the VLBA for a number of years. And so these are my toys, but I'm really going to talk to you about Antarctica. And what I'd like you to get from my talk tonight is, first, what's special about Antarctica? Why does every astronomer want to go to Antarctica to do astronomy? Where do we go and where do we do that type of astronomy? What type of research we do? And then I'm going to give you a rundown of the main telescopes that are in Antarctica and hit some of the more recent results from those telescopes, including the very early universe, some hunts for dark matter, imaging black holes, and the emerging field of multi-messenger astronomy. And I will try to answer any questions as they come along. This is meant to be kind of pedagogical kind of talk. So if you're an astronomer, where is the perfect place to put a telescope? Well, you want it cold, dark, high, and dry. Probably not the best place to bring someone on a first date, but Antarctica is a really cold, dark, high, and dry place. It's said to be the coldest place on Earth, and it's among the driest places on Earth. And technically, large parts of Antarctica are considered a desert. Of course, it has dark skies, no diurnal cycle, so long periods of dark skies. Something that I will mention a bit later, but the atmosphere is extremely stable and transparent. I'm going to talk a little bit about that transparency later. Most of the turbulent layer is confined to a couple of meters from the surface of the ground. And so if you can get the telescope a few meters above the ground, you end up with a very stable telescope. So typically you're talking about 3 to 10 times better seeing than some of the best astronomical sites in the world. If you're operating an interferometer, you get these beautiful coherence times, allowing you to image a large isoplanic patch. This is more technical stuff. And I'm going to talk a little bit about water vapor as a technical dive a little bit. There are some disadvantages. I'm going to go take a look at chat to see if any questions have come up. Nope. There are some disadvantages. One is obviously supply issues. And another thing you can see over here is aurora can get in the way, especially right at, near the ocean. The aurora can be quite strong there. And one point that's not well appreciated by people is that the sky coverage in this multi-wavelength era, not a lot of glass is pointed in all the same part of the sky that you can see from the South Pole. So it's not always the best location for comparing data sets from multiple telescopes. Nonetheless, wonderful place to do science. All right, so I'm not going to throw a lot of equations around or a lot of complicated plots, but I'd like you to see this one. And it's really kind of a description of why astronomers find this site so important for millimeter and submillimeter astronomy. Over here, I've plotted the atmospheric transmission as a function of frequency, and it runs from, say, 1 megahertz all the way to a few terahertz. And this is a atmospheric transmission from Mauna Kea. And it just crudely, the taller the windows, the more light it lets in. And as you well know, Mauna Kea is considered one of the best sites in the world. And the difficulty is that there's still some troposphere and stratosphere, even up as high as Mauna Kea. And there's water, oxygen molecules, nitrogen molecules in the air, in that air, and it absorbs. You get these very broad absorption troughs. I'm waving my hands around. You can't see my hands being waved around, but you end up with these broad absorption troughs to the point where you will actually block out windows of the universe by having these molecules. So by going to high elevation, you have less precipitable water vapor in the atmosphere. And so this is a measure of how transparent your site can be. Kitt Peak, typical PWVs of 1 centimeter, Mauna Kea is 1 millimeter. Now let's go to Dome A in Antarctica. I'll jump between these two just so you can see, whoops, what the difference is. It's about the same elevation. You see 4,092 meters, 4,093 meters, give or take. Here's the most important thing to take away from this. The best day on Mauna Kea, okay, the absolute best day you can get on Mauna Kea doesn't even get close to the worst day you can get on the Dome A site in Antarctica. A typical day is like 300 micrometers of water vapor. So that means is you get these very broad and high transmission regions that allow in light. So you can, and it's not just the fact that you now don't have to build a bigger telescope because the more light is getting through. The other thing is that you're opening up new windows into the universe. And these are two important lines for radio astronomers who are studying the evolution of galaxies, the carbon-2 line and the nitrogen-2 forbidden lines. These lines are important volumetric cooling lines for when gas is forming and hot gas is forming into stars. It radiates primarily through this. And so if you're looking at galaxies in the early universe, say at a redshift of 1 or 2, these lines turn out to be really, really important. And so in the Antarctica, you open up these new windows of opportunity. All right. So moving along, where do we do astronomy? And it really comes down to two fundamental sites that are permanent, the South Pole site and the McMurdo site. The McMurdo site is over here. Can you see my laser pointer? Laser pointer is showing you at the coast near the Ross Ice Shelf. So that's the McMurdo sea level site. And then there's the South Pole site, and that's the one I'm going to spend most of my time talking about. These three sites, Dome C, Dome A, and Dome F, they're under development. Some remote observing from there. Dome A is considered among one of the best astronomical sites in the world, and we hope to develop it in the near future. All right, a few pretty pictures just to set the stage here. These are the three telescopes from the south. Well, there's four. These are the telescopes that I want to talk about in the next few minutes that are at the South Pole. The first one is the BICEP array, and the second one is the Keck array, which has now been mothballed. The SPT, the South Pole telescope, and then this one, the most bizarre telescope of all, called IceCube. And this is the winter over crew. This is a shot taken just before Jay and Judy and I went off to see the Antarctica. This is the winter crew that was about to get on a plane and go home. All right, a few close-up shots here. This is the BICEP 2 array. This particular array, we'll get close-ups of this one later. This one is dedicated to studying the very early universe, looking for, and I'll tell you a little bit about the signature of the inflation in the early universe. This one over here is dedicated primarily, although it's got a more diverse program, it's dedicated for the hunt for dark matter. And this is just a fun shot of, on December the 4th, of the partial solar eclipse that happened, from that same location. All right, so here we are in the most bizarre telescope of all. It doesn't look like a telescope, and I'll explain a little bit later, but it's engaged in the multi-messenger aspect of astronomy these days. And for the last 10 years, it's been hunting for extragalactic neutrinos. I will come back to that a bit later. This is my favorite photo of the whole bunch because I find it terrifying. Just wanted to share it with you because you folks are from Winnipeg, so you're not not as terrified as I am. But you can go Google on YouTube a walk at the South Pole from station to dark center POV, and you'll see these flags mark the path back to the main station at the South Pole. And this is a shot taken from the BICEP and BICEP array. And during the long winter of the South Pole winter, you have to do this 1 kilometer walk by staying very, very close to these flags as much as possible. And I think when this shot was taken, the wind chill was minus 85 degrees Celsius. And I get texts from my friend Greg from Winnipeg all the time telling me how cold it is there. But I'm sure you would also, all of you guys would find minus 85 pretty cold too. All right, enough with the pretty pictures. Let's move on to a crash course in some cosmology, so I can illustrate some of the science that's being done with the telescope. Before I go on, is there any questions you want to ask about this yet? Because I'm about to do a deep dive in cosmology here. No? Okay. So we have a fairly remarkably simple model for describing the evolution of our universe. All right, we got a raised hand over here. Do you want?
Sorry, I didn't mean to interrupt. I just wanted to ask, do you know of any plans to use the lunar surface as I guess, the extreme case of no water and very cold temperatures in the near future to supplement some of the work that's being done here? I know they're talking about Artemis and all this other stuff, but just curious.
Yes, there's a number of projects, and I would say the one that's most interesting to me personally is the, I don't have the name of it off the top of my head. I'm trying to turn off this, hang on a second. There, okay, turn it. All right. The one that's most interesting to me is an attempt to locate very, very low frequency radio systems to look for the this so-called dark ages, to look for the signature of the dark ages. And there
you mean by being isolated from Earth there without the radio noise?
Right, from the radio interference from Earth. And I'm missing the name. I'll look it up. Maybe at the end of the talk, I'll look up the name of this. But there's some really honest good faith efforts to try to put these things on the dark side of the moon so that you can be free from the man-made interference. And I think that that's a project that could happen plausibly in the next decade or two. All right, so getting back to light line CDM, I said it's a very simple model. I didn't mean it makes it simple to understand. It's a simple model in the sense that it's the whole universe, and from the early days to our present time can be described by basically 6 free parameters. And that posits, of course, that the universe began 3.8 billion years ago, give or take, in a singularity, and that singularity expanded, and eventually that led to the universe that we see today. And this model is really quite remarkable. Here, I'll go back to my laser pointer. It can describe, as I will talk about in a minute, and predict the cosmic ray background. It talks about the dark ages, for which we have some handle on, and the origin of the first stars and quasars, and the origin of the structure, including the peak of structure at a redshift of 1 or 2, formation of galaxies, right to our present day, where we can see the dark energy expansion. So this model is remarkably successful model. And one of the cornerstones, coming back now to the 1960s, mid-1960s, is a so-called cosmic microwave background. So again, I need to understand that after that initial expansion, the universe cooled, and around 380,000 years, the plasma, the initial plasma, started cooling down to a temperature of about 3,000 Kelvin or so. And at that point, the electrons and baryons are able to stably recombine and form atoms. And at that point, the universe becomes, it's no longer opaque, it becomes transparent, and the photons and the baryons decouple. And prior to that time, there were these acoustical waves that were able to propagate into that mixture, and that it's not able to happen. And that initial density structure, that initial structure of the expanding universe, which is very, very small microscopic fluctuations, are the density fluctuations that led to the planets, the stars, the galaxies we see today. And the CMB makes the observation of the CMB is sort of a verification of that general model. The CMB is that thing that you read about, that 2.7 degree Kelvin in all directions signature that's left over from the Big Bang. Now, if you probe really, really carefully down at that 2.7, if you go down by another factor of 100,000, what you see is this picture here from the Planck satellite, which are the 2.7 Kelvin's been removed, and now you're just seeing these 30 microkelvin fluctuations. And these are the seed gas density fluctuations in the cosmic microwave background that gave rise to the galaxies and stuff we see today. All right, sorry, it's a long explanation for what I wanted to say, but I'm going to use one more step to be a little bit more bizarre, and then I'll go into the observations. If the CMB model is correct, and it's backed up by a whole host of data, it makes a very bizarre prediction, because when you look at that previous image, you'll see that it was very isotropic in many directions, and its geometry is quite flat. And in order to explain that isotropy, the horizon problem, various other problems that arrive in cosmology, physicists, gosh, 20 or 30 years ago, came up with something called the inflation model. And what is happening is, in the really early phase, just after that singularity, at 10 to the minus 36 to 10 to the minus 32 seconds after the Big Bang, there is this period of extreme rapid expansion. It's called the inflation period. There's 10 to the minus 32, and it fades out. And you need that in order to preserve that uniformity of that early universe. And that enormously rapid expansion gives rise to basically a stretching and messing up of space-time through gravity waves propagating through space and time. And that imprint, not just the acoustical waves that you saw in the early CMB, that is actually imprinted upon the polarization signature of the cosmic microwave background. So I probably lost 90% of the audience, so I'm gonna go back down a little bit here. The point being is, if one of the main predictions for understanding why our universe is so isotropic and uniform is that it's going to leave behind, if inflation is the explanation, it's going to leave behind a signature in the polarized light coming from the cosmic microwave background. And so the Antarctica has been the place for trying to look for that signature. And this is an early BICEP 2 telescope that I pointed out earlier, and that's a baffle. So many of you who are familiar with baffles. This is just to cut back on the background radiation. So there's been a massive race to look for the signature of inflation, and BICEP was the detector and the program that was developed to look for that. And BICEP 1 came along, BICEP 2, BICEP 3 is along. Successive generations of these so-called transition edge sensors, or bolometer arrays that image. And what they do is they image several hundred square degrees of the sky, as much as they can, very deeply, down way below the 30 microkelvin level, down to the few microkelvin level, looking for the signature in the polarized light. And that's traced by these little tick marks here, polarized light. And in 2014, they announced that they'd made a detection. And then they had to withdraw that detection. And if you ever want to read a wonderful story about what it's like to be in competition for the Nobel Prize, I would read Bryan's book here. I know Bryan. He's really quite a good writer, and it's a great story of getting involved in a big, massive project to look for this signature. So I can highly recommend this book. It's a fun read. But what it turned out to be was the foreground light from our own galaxy there's dust in it, and that dust rotates in a magnetic field in a preferential way, and it also has polarized light. And so what they were detecting was polarized light from our galaxy, not from the early universe. So very disappointing, and no Nobel Prize for you. So what they're doing now, and they've been doing for a little while, there's one more stage above the one I'm about to show you, is they've been using this old telescope here. It's called the Keck. Well, this is actually contains DAISY. It's a telescope called DAISY that was the first to measure the anisotropy and the CMB. But they've built a telescope that is not as sensitive as DAISY, but has many more frequencies. And so this has been working in partnership with the BICEP 2 and BICEP 3 arrays. So this telescope up here, the Keck array, can remove the dust from the data that's from BICEP 2. And as a result, they've been able to push much, much deeper down. All right, one more plot. And again, just to give you a feel for the state of the art that existed before I got on that boat with Jay and Judy, October 2021, and this has not been superseded. What they've done is they added the data from Keck. This is the imaging data looking for polarization, and they've not detected it, but they've got limits. And they published their work from all of their data up until 2018 in the October 2021 PhysRev letters, physical review letters. They don't have any detection. And a way to intuitively understand this is the relative amplitude of those space-time gravity waves versus the acoustical waves. So this is some measure of how much amplitude the inflation is. And then this down here is some measure of how long the inflationary period is, 10 to the minus 32 second thing, how long that was. And the available models used to coexist in this kind of phase space, but the dark blue bit here is kind of where they've got the models down in now. So they're narrowing the range of where the physical models, and they've already ruled out some of the models that are outside of this phase space. So they're making good progress, and we have reasonable expectation in the next few years that BICEP 2 and a telescope in Chile will be able to, BICEP 3, I mean, and we'll be able to make those detections. So that's good news. So that's the search for the early universe. Let's move on to SPT. So SPT is the South Polar Telescope. It looks more like what you would think of a telescope when you think of a telescope in the traditional sense. It is a little different for those experts. It has an offset Gregorian feed. You see that most of the instrument package is down in here. We do that with our telescope in Chile also. We have these offset feeds because we don't want to have any feed legs in the aperture. We want to minimize any scattering in the main aperture. So we want that whole main aperture to be completely unobscured, no diffraction rings. It's optimized for wide field imaging, the detectors that are there. Again, they have these TESS transition edge to sensor detectors that I don't know very much about, but they're state-of-the-art bolometer arrays. And they've been, every winter season, they go out and they image more and more of the sky down to 3 microkelvin at arc minute resolution. All right. So their science program is more varied, as I mentioned. I'm only going to talk about dark matter, and I'm going to talk just briefly about the direct imaging of black holes. So they're engaged in the search for dark matter. And the way they do this is a technique called the SZ effect. Excuse me. The cosmic microwave background, which I already talked about later, is they are looking for dark matter in galaxy clusters. And here's a toy model of what a galaxy cluster looks like. Galaxy clusters are the largest gravitationally bound structures in our universe. They consist of hundreds and sometimes thousands of galaxies, hot gas, and lots of dark matter. And so here's our little astronomer in the South Pole with their hat and gloves on, and they look in with the SPT in this direction. The photons that are coming from the ubiquitous cosmic microwave background, some of them propagate through this this cluster and the hot gas, and they get a little extra boost of energy via something called inverse Compton effect. And that slight shift in energy between the cosmic ray background that doesn't go through a cluster versus the one that doesn't gives you a slight kind of kink in the spectrum. And you can measure that. And magically, the nice thing about the SZ effect is it's completely independent of redshift. So you can see these clusters from a redshift of 0.1 all the way to a redshift of 3, 5, whatever. So it's a really wonderful technique for counting up the number of clusters in the early universe as a function of redshift. And that turns out to be quite an important predictor for various dark matter models. So in its spare time, when it's not hunting for dark matter, the SPT takes part in a global array to image black holes. And I know you've seen the results of this. I wanted to give you kind of a really quick overview of how this works. What this is doing is we are combining the SPT with telescopes around the world, sub-millimeter, millimeter telescopes around the world, to synthesize an aperture that's equivalent to the largest diameter telescope whose diameter is equal to the largest separation between telescopes. It's the Greenland telescope and the South Pole telescope. ALMA is the telescope that NRAO runs with ESO and the Japanese. And this is the biggest one in the array. It's much bigger than anything else. And the way to think about how interferometry works without going into Fourier transforms and Van Zittig-Zuricki theorems is imagine you're the radio source looking down on the sky and the Earth is rotating. These telescopes are carving out circles on the sky as you see them, and they're carving out an aperture that's equal to the, as I said, the largest diameter. And by using some fancy techniques, these are the telescopes that are used in that array. We can directly image black holes from M87 and from the center of our own galaxy, Sagittarius star. And so I know you've all seen this image. This is a very famous image of the accretion disk and black hole, event horizon around M87 from this same array that SPT participated in. And just to put it in perspective, you can drop our entire solar system right into this spot right in here. So this is that beautiful image. Now in March 2021, you might not have seen SPT's contribution to this same image, but with polarized light. So here it is in here. These lines, Jan English at your local university, who I know very well from Toronto, is really good at making great visualizations of this kind of stuff. But these are tracing magnetic field lines, these wisps of things here. And so for astronomers, understanding the magnetic field in accretion disks is really, really important. Both the strength is important and the geometry is very important because they govern how material gets into a black hole and how jets are formed, that some of that gas which is escaped. So this is a wonderful contribution of the SPT and other telescopes for doing worldwide interferometry. Okay, so moving on to how am I going for speed? Am I going a little too fast, a little too slow?
I think you're going okay.
Okay, I've got, let's see now, maybe 10 slides at the most.
Oh, you got lots of time.
Okay, well, I was hoping there'd be lots of questions and I'm happy to answer questions. So, I've talked to you about dark matter, the search for dark matter with the SPT, very early universe with the Keck array and BICEP. Now I'm going to move on to the truly most bizarre thing of all, which is the telescope called IceCube. Until recently, you know this, pretty much everything we know about the universe comes from optical light, radio light, and gamma rays. But in the last 10 years, say, there's been a move to studying what people call an awkward thing, but it's called multi-messengers. But it means using things like neutrinos and cosmic rays and gravity waves through a telescope like Virgo or LIGO, the gravity waves. So to study the universe and things that are not photons. And gravity waves, that's the displacement of space-time, the distortion of space-time. Cosmic rays, you know, these are ultra-energetic charged particles. And the neutrinos, which are the most common particle in the universe, but almost don't interact with any particles at all. I've read somewhere, and I hope this number is correct, but there's about 100 billion neutrinos streaming through about a cubic centimeter of your body every second. That's about the size of your pinky, right? So neutrinos are very abundant, but they really don't like to interact very much. And in fact, there's a phrase when a new postdoc comes through, and they might be a little shy at the observatory, I call them a neutrino. And so we try to make them interact we try very hard to make them interact, because these postdocs can be very high energy, but they have to interact. So we do have an understanding that the highest energy, at least predictions, that the highest energy neutrinos are produced deep within black holes, exploding stars, and they're under conditions which I'll talk about in a minute, where you just cannot duplicate on Earth. We're talking about gamma ray bursts, which I worked on, supernova, which I worked on, and active galactic nuclei, neutron star mergers, which also give rise to the gravity waves. So this has been an ongoing revolution in the last decade or so. Nobel Prize has been awarded for various aspects of this, trying to understand the universe just beyond photons, but understanding it in cosmic rays, gravity waves, and neutrinos. All right, so the question is, how do you catch a neutrino? They don't interact, they're very weakly interacting. Well, to build something like IceCube, I don't know how many people know about this telescope. I'm fascinated by it every time I read about it, every time I read a paper about it. It's the largest and most expensive telescope in Antarctica. It doesn't look like a telescope, and I'll show you a picture of why that is the case. The real telescope is underneath this conning towers here in the main building. And the telescope is really a cubic kilometer of ice. It's called IceCube, of course. And the other fascinating thing about IceCube is it doesn't look up into space, it looks through the lithosphere. It looks through the Earth. It is imaging, it is using the Earth and the ice above the solid Earth to block the energetic particles that would otherwise be a background. And it's sensitive to 100 TeV to 1 PeV. And I looked up today, just to give you a sense of that, CERN, the accelerator we have on the ground on Earth, the biggest, highest energy that CERN has is 13 TeV. So this is really looking at things that are at the extreme end of the energy spectrum. And the event rate of truly energetic events is low. It's like 30 per year that they detect. The trouble is that the background radiation, the background event rate from particles streaming in all directions is about 2,500 per second. So they have to be able to, out of those 2,500 events per second, they have to be able to detect 30 genuine events. And they do that through this following thing here. Here's on the top of this diagram here, you can see on the ice top, that's the main control building. And what they've done is they drilled 86 multiple kilometer depth holes into the ground, into this region that's about a cubic meter across, that has had several kilometers down right into the Antarctic bedrock. And attached to each of these strings are these photomultiplier tubes. And they're using a Cherenkov radiation technique, because what's happening is I'm waving my hands around, you can't see me, but what's happening is the neutrinos are coming in from the bottom of the Earth. They are interacting with the ice, rarely, but there's enough of them that they will interact with the ice, and they create a flash of optical radiation because they're moving with respect to the ice faster than the speed of light. So it's called a Karakas radiation technique. That flash is picked up by these photomultiplier tubes. All right. So briefly, what they've learned over the last decade is in order of, let's say, believability, or what's a kinder word than that? Confidence, let's say, I wrote it down here. In order of decreasing confidence. So the one thing that the IceCube has established that everyone agrees upon is that the various highest energy neutrinos above, say, 100 TeV are extragalactic. And this is the distribution of their events. So as of 2016, each of these represents an event. Here's the galactic plane. And these events are completely isotropically distributed on the sky, at least the part of the sky that they can see. And so that can only be created, you don't see the galactic plane. So they're not a galactic population, you don't see the ecliptic. And so that can only be created by a population of sources that is out there at a high redshift, at modest redshift. Not in our local galaxy, not in our local group. Now, with one exception, we still don't know what the sources of these neutrinos are. In one case, down in here, we saw a flaring gamma ray and radio source. There's an active galactic nucleus called a BLAC that had a coincident neutrino. And astronomers have argued, and the evidence isn't all that great, 3.5 sigma or so, that the neutrinos and the gamma rays flare and the radio were somewhat coincident. And we're starting to add a few more of these events, but the bottom line is we still don't know what the source of these neutrinos are, these extragalactic neutrinos. We just don't know. They could be in the black holes of these BLAC objects, but they could be related to something else. Because these error circles are quite large. They're well, you can see some of them here. This is a well localized one, but they're typically errors much larger than the full moon. Many full moons in diameter that a piece of the sky you have to search. And every once in a while you see a paper. I saw one in March about some hints of some exotic and new physics coming out of IceCube. The burden of proof, at least for me, seems pretty high. Latest paper showed up in Nature about a possible something called an antineutrino through the Glasgow resonance. And not sure. I think I want to see a couple more of those things before I would accept that they're seeing new physics or verifying some old predictions of antineutrinos. All right, so I wasn't sure I was going to have time to do this one, but I do apparently. So I will talk about the final thing, which is focused right now. Previously was on the physics being done out of the South Pole, the astrophysics. There's another station here that I told you about, McMurdo, which is on the coast. And what it has going for it really is that you can launch balloons from there and the balloons stay up for a long, long time. This is a summary of the 40 flights that have been flown out of there for, say, 30 years, I think it is. Yeah, 30 years. And you can see they reach an average altitude of 35, 40 kilometers. And they can stay up for a month quite easily. And they do so in this very predictable, very stable way in a westward trajectory. And they're very easy to find because they land on the ice. They don't land in, China or some other difficult place to get to in the water. And so this has been a really great site for launching balloons and especially testing out prototype instruments for space and things of that nature. And my favorite one is from a colleague of mine. He operates, he hasn't for a number of years, but he operates a radio version of the IceCube experiment. And you can see his little experiment here. And you can see the balloon getting ready to launch. This is called Anita, and it is doing the very similar thing to IceCube, but it's using radio Karakas radiation, radio flashes. So what they do is they launch the balloon and they use all of Antarctica, the ice sheet of all of Antarctica as the detector, looking for flashes coming from the Earth, from ultra high energy neutrinos. And they haven't published in a number of years, and I don't think they've made any detections yet, but it's a fascinating experiment. All right, so what's next? Briefly, and I haven't got any updates on some of the things. We've just, when I was about to go to Antarctica, the summer crews were just arriving. And in the summer, they do a lot of maintenance because, of course, they've been operating almost the whole time while it was dark. And so large numbers of people flow into there in the summer. They do their upgrades too. So they maintain the instrument, they fix everything all up. And winter's for observing. There's a skeleton crew. They're just starting to go into the winter observing mode now. And the winter over crew has come in there. I think it's a small group, as I pointed out, about 60 people at the beginning were in that initial picture. And for the BICEPT array, which I showed you about, there's been multiple generations. And they now have the BICEPT array, which is 4 versions of these BICEPT telescopes. And they're all the same, but they're all mounted on the same platform. And they now have, I think, they much more frequencies. If I remember right, 3 or 4 different frequencies. And all these telescopes are connected together to give you a very large multi-frequency image of the sky. So they don't need the Keck array anymore to image the dust. They can do that by themselves. And as I said, the prospects look good for them in the next several years of beating down that systematics in that plot that I showed you to actually find that inflation signature free of the dust from our galaxy. I don't know the status of this. When I was reading about this stuff in the fall, they were going to install a new camera on the South Pole telescope, just a bigger camera, much faster, same type of detectors. And I wasn't able to find out how much progress they made in their summer. But hopefully they did make progress, and they'll start winter observing with that and speed up the hunt for dark matter. And then IceCube generation 2 is, they're still photon starved. They're still signal starved. They only detect 30 neutrinos per year. And so they're hoping to do an upgrade because the hunt is on to figure out where these bloody neutrinos are coming from, to identify the sources. Are they gamma ray bursts? Are they AGN? In many senses, they are, still have a decade to go or so before they can really turn this into a field where you're studying individual objects. They have to have the sensitivity to be able to see a neutrino and be able to pinpoint where that neutrino is coming from with great accuracy. And that I look forward to. And then finally, this is a shot of one of the last aircrafts leaving. I think the shot was taken this week. It's leaving the South Pole, going past those wonderful sub-millimeter telescopes, and for the long winter ahead for observing. And thank you, everyone. Thank you for listening. I'm done.
Well, thank you very much. Now, do we have any questions? I think Darren put up his hand.
As always, I have a question or two. Thank you very much for the great presentation. I really appreciate it. It's very enlightening. Quick question for you. Well, actually, I've got 2. Number 1, can you wind back to the slide where you had the initial cosmological expansion? It was one of your earlier slides, like maybe second from the beginning.
Yeah, let me just hang on. When I was describing the...
It would have been way back. Probably, yeah, just, let me see here. It was near the, yeah, there it is. That one there, modern cosmology. Antarctic frontier, number 14. Yeah, that's it. Okay, so I have a question for you, and I'm a bit rusty on my cosmology, I'll be honest. It's been a while since I've taken astrophysics, dedicated, probably 30 years now. But, learning a lot over the years. Your dark ages point there, and just getting the afterglow light pattern part of it. What are the things happening in the dark ages? Is that where they're getting cold condensation of matter before gravitational attraction ignites it, and then you get the first stars? Is that kind of the idea?
Yeah, so I'll give you the perspective of the dark ages from a radio astronomer's perspective. At that time when the gas is cooled to 3,000 Kelvin, and it's mostly hydrogen, but of course there's some lighter elements too. The first stars have not formed. So it's called the dark ages because there's no luminous sources of material there. No new stars, no quasars, no black holes, nothing like that. And the gas is mostly hydrogen. And it's warm hydrogen but cooling down. So it's said to be dark ages because those fluctuations those early fluctuations have not yet formed the first stars. You might have heard a phrase called population 3 stars.
Right, no, fair enough. But here's the question I have for you here. Now, this is related to this. So this period that, they say approximately 375,000 years. Now we have a mic going on here. I keep hearing a banging here. It's not me, I don't think.
Not me.
Okay.
I think Jim's got his mic open.
Jim, can you turn off your mic, please? Mute it.
And let me just point out while I remember, the dark ages are also that time. I mentioned about the fact that we were trying to build telescopes on the far side of the moon to look for the signature of the dark ages in redshift and neutral hydrogen. And that's precisely what we've been trying to do, is to build telescopes that would see that redshifted hydrogen that emits at 21 centimeters, but down at this redshift would be much, much higher.
Right. Now, here's my question. As you get quantum fluctuations and this inflation and things settle down, and I know there's a little bit of error bars for the 375,000 years, is it potentially possible, because obviously the 3,000 Kelvin mark is where you're starting to see stable hydrogen atoms and then eventually helium and so on. Is it potentially possible that there's a little bit more in play in that early stage of the universe that we're not quite getting yet? Because I'm kind of wondering now, you're seeing this new neutrino source of rich neutrinos. Is it possible that that could be kind of indicative of this sort of early region of, let's just call it cooling period that you may have detected, almost like the center of the bang, if you will? I know that's a little bit crudely put, but something along those lines.
Before the CMB, the universe is opaque, so it's very hard to see beyond that. After the CMB, after you didn't claim otherwise. I didn't mean. The neutrinos that I'm talking about are probably coming from very nearby by my standards, by redshift of 0.5 or something, really, like in our backyard practically. So it's sort of down in this region right in here. Neutrinos are probably not coming from in this phase right here. What I think what you're asking is, could there be some new physics buried in here? I think absolutely, absolutely. One of the things that we're discovering in cosmology, and it's worth looking up if you have a fascination about this topic, is there is this Hubble tension. It's called a Hubble tension that's going on right now. I went to graduate school with Wendy Freeman, and she measures Hubble constant with Cepheids. And then other people have used cosmology probes like Planck to measure Hubble constant. And they're starting to realize that these different methods are measuring different values of H0, and the discrepancies are getting to the point where they can no longer explain them away from error bars. And one of the, now this is just speculation, so you don't get to see me waving my hands, but I'm waving my hands. But one of the things that they're looking for in this early universe is perhaps hints that there might be an extra source of dark energy that is helping explain this Hubble discrepancy. So there's many ideas, and I'm about looking for new physics buried in this thing. But I would urge us to get more data, in particular, get the telescopes capable of imaging those dark ages, because the nice thing about the dark ages is you can slice it like cheese. You can look at that redshifted hydrogen at multiple redshifts, and unlike the CMB, which is just a snapshot of the point of the universe when it went optically thin, the dark ages has a thickness to it in redshift space that you could cut through. And I think if we were able to cut through that sliced cheese and we'd be able to fit
there should be a lot of rich data in there, hey?
Should be a richer data set in there, and an ability to reject certain models as a result of that. It's not my area of research.
No, but fair enough. I just thought I'd ask. Thank you. Appreciate it.
Right. Yeah, thanks for the question.
Michelle and then Ed. Michelle, go ahead and ask your question.
Oh, I had put it in chat, but
oh yeah, yeah. Well, IceCube can detect all flavors of neutrinos. I don't know the answer to your question. When I don't know the answer to your question. That's basically it.
okay. Yeah, no, I
I'm
had
just wondering off the top of my head, because again, I'm not an expert in that topic, but how do you know when you've seen a certain flavor of neutrino versus one flavor versus another?
Yeah, well, I worked on Amanda, and
Yes,
it's a certain signature you see for tau on neutrino, and I knew that it had some sensitivity to that, and that they were using the Earth as a filter. So they were looking for new kinds of physics. So I knew that was one of the things, but I haven't really been following since. So I thought maybe you had known.
Yeah. Had they made a new discovery of a flavor of neutrino, then I would know about it. If there were people out there making claims that they might have detected it, I wouldn't know that.
Yeah, I think they were just looking for exotic sources of neutrinos.
Yeah, it was recently their 10th anniversary, and so it's very easy to go out and find, the list of their best discoveries made, and I don't recall that was in their work.
Well, someone left me a link. I'll have a look at that.
Yeah.
Sorry.
Yeah, for me, the isotropy of the isotropy of the sources is really quite important. As I showed you earlier, don't underestimate how, well, I know you don't, but this is really quite significant that they're able to trace this to a population of sources that's distributed isotropically. That's really quite important. Neutrinos are not charged, and so they don't get deflected by the intergalactic magnetic field. So they're coming directly from their source. Cosmic rays, as another multi-messenger, they get deflected by magnetic fields. So they don't point back to their source at all. They're harder to pinpoint. So this is really important. For gamma rays, which I worked on, it took us 30 years to figure out where they came from. Even though we knew they were isotropic, it took us until 1997, 25 years ago, to actually pinpoint them and tell them, that the gamma rays came from the birth of black holes. So the isotropy is quite important, but the upgrade of IceCube from Amanda to IceCube to the next generation IceCube will probably allow us to pinpoint them better and make a lot of progress.
It's pretty cool.
All right, I believe Ed's got his hand up. Ed Wright.
Yeah, I do. Yeah, thank you. I have two questions, and they're probably much easier than the other ones. I just wanted to dig just a little deeper in a couple of things you had said. One of the things you said, Dr. Frail, is that they've determined that the TeV, I guess that's trillion electron volt neutrinos, are extragalactic, and they are from high redshift. I'm just wondering if you could explain how they were able to determine that they are extragalactic and how the redshift fits into that.
Yeah, so they're not measuring a redshift. Imagine, if you will, let's go back to gamma ray bursts. For a while there, we didn't know if gamma ray bursts were in our galaxy, in our solar system, or in the general universe, out in the general universe. Let's imagine that gamma ray bursts came from comets, okay? Then if you mapped out the distribution of the gamma ray bursts, they would be concentrated in the ecliptic plane, or with some tilt, right?
Right.
These things are not in the ecliptic plane, okay? Which I think is caught by this dotted line, although I'm a little rusty. If they were, and people thought about this, if they came from a population of neutron stars, they'd be concentrated in the galactic plane, because neutron stars come from those stars, and those stars explode, and they're massive stars, and so they'd be concentrated in the galactic plane. Maybe they'd be a little thick, but they would still be in the galactic plane. You're not seeing them in the galactic plane, these neutrino sources. Instead, they're seen everywhere. They don't seem to have a preferred direction. And that's why we argue they have to be far away. Is that clear?
Yep.
It's the isotropy that argues that they're extragalactic. Not, I don't have any distance information on these at all, except for this guy right here, except for TSX 0506 plus 056.
Okay, great. Yeah, no, that totally.
One of the things that I do now is if you want to get telescope time at the VLA, you have to write a proposal every, along with several hundred other astronomers every 6 months. But I sit on the committee that does director's discretionary time, and we occasionally get proposals in class. I have one sitting in my mailbox right now from an event that went off last, let me see now. 2 weeks ago. And they think it spatially coincides with a BLAC object like this object right here. And so they want to be able to get on very quick to see if they can see a simultaneous, not simultaneous, but if they want to see if the radio is rising at the same time as the event was active and gamma rays and active neutrino. So this is a very, very contemporary topic. As I said, this weekend I'll be reading proposals on this topic right now. I'm trying to find the origins of these neutrino sources.
Yeah, that's very cool. Just want to
get any more state of the art, contemporary. Yep.
Great. Just one other question, just real quick. An earlier slide, you said that photons that pass through a galactic cluster get a boost in their spectrum. I'm just wondering if you could explain how that happens.
Yeah. All right. So this is the SZ effect. And the hot gas is, think of it as a bunch of particles moving around very, very fast. Okay? Temperature of 10 to the 7 Kelvin. And these are the photons coming from the cosmic microwave background. The photons scatter off the electrons and pick up a small amount of energy from the electron. It's a little bit like a, bad analogy, but a little bit like a pool ball picking up energy from another pool ball. Okay? So these are hot electrons in this hot gas that give up a tiny bit of their energy to the photon and boost it, called inverse Compton. Compton is a man, a scientist who studied the Compton effect. And so these little red photons get to be redshifted to blue photons by the fact that they interact with the hot gas in the cluster. And the hot gas and the dark matter and the galaxies are all part of that same, not globular cluster, but galaxy cluster. These are clusters of galaxies. And so you, the astronomer sitting there, again, with your hat on, you're going to see in this direction a tiny little shift of the light from you're going to see the cosmic microwave background spectrum, but in one location, you're going to see a little kink in that thing. It's going to be tiny, and that's going to allow you to detect the cluster at any redshift. And there you have the redshift information. There you know what the redshift is. I got some raised hands.
Makes sense. Thank you very much.
Sorry, I'm just going to build on Ed's question here. Is it possible that that series of photons coming from this hot gas cluster is actually not re-emitted or re-energized photons, but actually energy coming from the gas itself? Because how can we distinguish those two? I mean, there's no way to know that for sure.
Yes, so that gas, the radiation that comes from gas that's like 10 to the 7 Kelvin, that's going to emit thermal Bremsstrahlung, but that's going to emit X-rays. So you can tell the difference because this is the microwave background, which is, 50 gigahertz or so kind of radiation. So that's the radio. This is, I'm pointing at the screen, sorry. So the hot gas, it's going to emit in X-rays. The gas that gets boosted, the photons that get boosted are going to be emitting at radio waves. So you can distinguish them quite easily. These little blue photons are only getting a tiny little extra kick of energy, and they're getting a kick of energy from the hot electrons that are mixed in with the hot protons. Yeah, that's where they're getting it from.
Okay, thank you.
And the magic part of all this is that that you can see this cluster independent of the redshift. You don't normally, when you look at an object, as you get further and further away, the light gets fainter. But the background light is what the important thing is, and that is already at the edge of the universe, so it doesn't really have a redshift dependence. As I said, if you count the number of these clusters as a function of redshift, that gives you a measure of how much dark matter is in the universe and how it's evolved. Is there one more raised hand?
No, I believe that was Darren was the last one.
What's the lowest temperature in Winnipeg ever?
I'm not sure. Jay, are you there? Jay might know. What's that?
Jay says minus 40.
2 point something.
2 point something.
Yeah.
But I don't.
Okay, that's impressive. I would urge you to look up that YouTube video. It was really quite a treat to see them. Where is it now? Yeah, going back here. It was really quite a treat to see them walking through that snow. And I have forgotten what it's like to walk through snow that's cold, the noise that it makes. You guys are all familiar with it, but I had forgotten that noise, that squeaky noise.
Mm-hmm.
Aren't those flags also in case you get like a lot of snowdrift and stuff because the visibility is very low and it helps you find your way?
They don't get a lot of snow there. They do have drifts around the main structures here and they have to plow around them, but they don't get a lot of snow buildup. So those aren't depth markers or anything. And I'm sure, I don't know for a fact, but I know that I would not make that walk unless I had a digital device in my jacket. So I don't think they absolutely need, the flags to find people, but.
I had two more little kind of related questions to Ed's there, if I can quickly add.
I was just going to add
diagram you had before.
Going to add to the flags, but okay.
On the diagram that you had with the hot gas, yeah, I was going to ask you what the scale of that is. Like what kind of scale are we talking about angularly, I guess?
It's not that one.
Yeah. The one that Ed was talking about with the hot gas, yeah, that one. So if you're looking here in Antarctica and you're looking there and you're talking about these large scale galactic clusters with hot gas in between, what are you talking about scale wise? Are we talking like
arc minute? Arc
minute? Okay.
Yep.
So, okay, that makes
one
sense.
Or two arc minutes are these things.
All right.
And whereas the cosmological signature, the early universe signature, the signature that I showed you here, that's occurring on scales of a few degrees. So one of the things that the South Polar Telescope does is it finds these clusters that represent a background contaminant to the people looking for the early universe signature. So they have arc minute resolution, whereas BICEP has half a degree resolution. And so SPT, I showed you here, what's their science called? One of the things they do in SPT is they help, helps BICEP remove the foreground clusters because clusters are an annoyance to them in their search for gravitational waves. Remember, the inflation is occurring, at that same era of the CMB. The imprint of inflation is occurring at a much higher redshift than where the clusters, the galaxy clusters are. So they represent a foreground. Not a great foreground, not a serious problem for them, but nonetheless, when you're getting down to these levels, having the SPT there to help them tell them where the worst clusters are. One person's noise is another person's signal, as they say.
Gotcha. Thanks.
So I have a question for you in the chat, and it says, how are the telescopes stabilized in the ice? Do they have to be periodically aligned?
I don't know the answer to that question. I wonder if they have to sink something down. They're obviously not going to sink it down to the bedrock. That's a really good question. I mean, that's a heavy telescope we're looking at here. I'll have to do some research on that. I'll have to look that up.
Okay. Michelle, I heard you had something you wanted to add about the flags.
Oh, I was just saying, in the winter, they actually have what's called a rope line. So the flags are connected by ropes so that you don't get lost when you're going across the station. The station's about half a mile across. So that's all I was going to mention. And when I was there, they didn't have the flags out in the summer. They had them out in the winter. And there was a gap between them to go across. And one time I decided I would just walk from one place to the rope line, and I actually walked through the gap and missed the rope line. But luckily there was another building, so I found my way back. But yeah, it's there for safety or storms. Yeah.
So does anybody else have any questions for Dr. Frail? All right. Well, Dr. Frail, on behalf of the RASC Winnipeg, we thank you very much for a really, really excellent talk tonight on the astronomy down in Antarctica, and gives us a different perspective of all the research that's going on down there. And we thank you very much.
Thank you. Thank you for letting me talk.
You're most welcome. And for all the rest of our members, that brings us to the end of the meeting. What will happen now is there'll be some people who can stay on, and with the stayed on, so you can chat and visit and see how everybody is doing and catch up on things, and have a very nice evening. I unfortunately have to step away and go to another phone call. So have a very wonderful evening. And as I mentioned, there should be, hopefully in about a week, we'll be sending out some information on Astronomy Day and how you can participate and support that. So have a great evening, and we'll talk to you soon. Good night, everyone.
People staying around?
Hello.
Hi, Karen. Long time no talk.
Strange.
Can you hear me okay, or maybe your audio is not working?
Ah, my ear.
All right, who's got that mic that's doing that? Is that you, Tiffany?
Might be Tiffany.
I don't. Oh, maybe my arm's right. Sorry about that.
Hang on a second.
Mike, do you think you could operate at those temperatures? Think of the stability.
You think I can operate at those temperatures?
Just imagine what you could get. Everything would be low down in the north, but
yeah, it's going to be a challenge between if I can operate those temperatures and if the equipment can operate those temperatures, because my goodness, my laptop would be one ice brick.
I know the astrophysics people advertise that they have their mountings at the South Pole, but I'll bet they don't send them the standard California temperature mountings that they give the rest of us.
They must have a special kind of grease on those gears for sure.
Yeah, I was going to say, Mike, that was the one thing you didn't mention tonight is the cold temperatures and what you need to do to, well, maybe you did. I missed part of it maybe, but hi, Karen. Haven't seen you in a while.
I've been around. I've been
good to see you.
I haven't been able to do much observing. It's been like either too cloudy or too cold.
I hear you on that one.
Yeah, I'm just hoping that the snow will
You're
start
gonna have
disappearing.
to join you're gonna have to join our Bino group. We haven't seen you log in yet.
Yeah, I've been just crazy busy with things right now. I'm doing a math upgrade through distance ed right now, getting my my pre-calc. So every night. What?
Congratulations.
Yeah. Yeah, I passed my first quiz. Yeah, got 100 out. I got 10 out of 10 on that one, and so 18 more quizzes to go. Yeah, when I was in high school, I was signed up for pre-calc, but it conflicted with band and choir, so I had to drop it.
So this is more for personal interest then, hey, than
Yeah.
anything else, I assume?
Well, I'm turning 65 in August, and then I get free tuition at the U of M.
So if you turn 65, you get free tuition at the U of M?
Mm-hmm.
That's good to know.
So I'm signing up for a BA, and then if I don't completely burn out working on that, maybe I'll go for a BSc.
Really used to offer.
I'm toying with the idea. I'm toying with the idea of going for a degree in biochemistry.
Are you doing your biochem?
No, I'm thinking of it. I'm toying with going part-time. I'm thinking of writing him a letter this year. Ah, my ears. Whatever's going on.
What is that weird sound? It sounds like gurgling.
The creature from the Blue Lagoon, I think.
It's weird, eh?
It'd be the cosmic microwave background.
Yeah.
I'll mute myself just to see if it's silent for a bit. I don't see why it would be, but
That's better.
yeah. Really? Fascinating. Okay then. Well, I guess I will bid you all a good night then. This has been fun. I've never attended a meeting.
Looks like your camera lens is a little frosted.
Foggy too. Yeah.
It's an old laptop. My phone is better, but then I don't get the view of everything. So okay, well have a great night, everybody.
Thank
you too.
Night, Tiffany.
Bye.
You all.
Bye, Tiffany.
And Kathy, you guys have to join our Bino group too. You have Binos, so you better
Yes.
sign in. Better sign in, please.
I think that was an order.
Okay, Dad.
All right.
All right.
Yeah,
We need to.
How
Go
many
ahead.
members strong are you, Darren? In your
I'm
Bino
sorry,
group?
what's that?
How many members strong are you in your Bino group?
Well, it's about maybe 8 right now. I mean, if we count Scott and everybody, I mean, I've had a few people indicate that they've been interested, but they didn't like actually formally say, hey, I'm interested in joining. So I'm trying to keep them moving along. Actually, let me think now.
Since you
Okay, we got Robin, James, me. So that's 3. Kyle is 4. Jason is 5. Luxton, Kyle's son is 6. Yeah, about 9. 9 so far.
What am I, chopped liver?
I'm sorry. Yeah, well, no, I didn't forget about you.
really?
No, I added you into the mix. So yeah, but it's about 9 or 10.
Yeah, I wonder.
Maybe closer to 10.
I'm just trying to figure out how to get your pants into the screen.
And no, you're not chopped liver, Michelle.
Oh, where's that come from? I forget the name of the comedian, but anyway.
Mike, I was just going to mention, well, first thing I was just going to say, excellent presentation. That was great. I learned quite a bit out of that. That was wonderful. You saw that message there from that text from Kamala. I don't know if anybody's gotten back to her, but it's kind of ironic that, and not in a great way, but Dennis goes, we're looking for volunteers, right? And then, it's been kind of sitting there for a bit. So I'll have to get somebody to get back to Kamala because we don't have a volunteer coordinator right now, I don't believe.
I don't think so either. And it's
No.
too bad because Astronomy Day is coming up, and it would be nice. We're finally coming out of a 2-year hiatus with COVID.
Yes,
It'd be nice
that's
to
right.
jump on it.
Yeah,
But
that's right.
Scott did present an interesting option for us to do something with the planetarium, on the Saturday, and more like a First Fridays event. I think he was talking about. In the Exchange District. So it'd be a neat idea to have people out, kind of like a real sidewalk astronomy idea.
I think Scott said Astronomy Day was in May the 7th.
I think, is it the 7th or the 8th? I think, but
whatever, it's in May, or I think Dennis said April.
But he was thinking about doing it on the first Friday. We could take advantage of that. Yeah.
Should be able to do something, even if it's only a couple of people.
Yeah.
Yeah. You know, this would be a fantastic opportunity, you know, with COVID to use that scope that Jay had at one time. I'm not sure if he still has it, but you know that
TV scope.
It's on loan to Andrea Meisner, but I'm pretty sure we could get her to bring it or loan it back.
Yeah.
Give it back.
Give it back.
That's a fun toy.
Yeah.
You know, with COVID being what it is, I know it's going down. After 2 years, I'm still kind of reluctant on having somebody look through my eyepiece. I don't know, it's just something about it, you know. You did well. It's just, again, it's not just a looking through. It's, you know, a lot of, you know, people will grab the telescope and they'll grab it by the eyepiece. I suppose maybe it's overly paranoid, but it's I suppose by May 2, it'll be that much less of a concern, right? But I guess I'm just saying there's some residual resistance to it. You know what I mean?
Yeah.
Isn't it funny how COVID has changed our perception? Because I mean, 3, 4, 5 years ago, you wouldn't think twice about that, even if somebody had a little sniffle
or a big sniffle. Come on, people
or a big
show up
sniffle
at work. Horrible.
You know, I did one astronomy viewing session, public observing session, and one little tyke came up to the telescope. He looked at the eyepiece and he engulfed it in his mouth. He put his whole mouth.
Oh no.
It's okay. We were out at the planetarium and Stan had his daub there, and it was tilted up at about 80 degrees, and some kid threw his empty Coke container in it.
Oh no.
Well, you know what? It's really funny. I was just talking to a buddy of mine in BC about that, and he was thinking of doing a funny cartoon with a daub and a recycle bin sign symbol on it.
Yeah.
Sorry.
Anyway, on the volunteer thing there, Mike, yeah, we need to do a better job of coordinating, like an intake coordinator or whatever for volunteers. So yeah. I've just, this week I've just been totally below water with work and stuff. So I haven't had a chance to do anything, but
well, you do a lot, Ed. You do a lot of work for the center, and really appreciate what you do for the council.
Oh, it's not, it's not that much, but thank you. Yeah. But yeah, somebody will have to get back to her.
Be online.
Yeah, it's a shame not to do it because she's anxious, she's excited, she wants to be part of it. So you want to embrace that excitement.
Yeah, for sure.
So I think I thought she volunteered to help with outreach stuff. So we could just get her involved that way, since she wants to know people. We should just say, well, we're going to do astronomy day and first night.
Yeah.
Why don't you come along and you can help organize it?
Mm-hmm.
You know?
That's good. Anything to get her started, right? And anything to engage with her, because it can flower into something, like you don't know what it's going to flower into, but definitely between her, whatever she has to offer and whatever the group needs,
right?
All you got to do is start. It's like anything. If you don't, take a step in and just start. Doesn't have to be right the first time.
I think she'd bring her husband and her son along, if not her daughter too, because they were all quite interested. Remember, her dad or her husband drove the son back to the city for some kind of soccer game or something in the middle of Spruce Woods, and then went back out.
Wow.
So they're committed.
Wow.
Yeah, we'll have to embrace that. I'll go back in that email trail and I'll just send a note back to everybody and just say, is somebody gonna talk to Kamala and see what she'd be interested in doing.
Well, I can just email her if you want.
Okay, sure. Yeah, I think that would be great.
I think Gord was trying to get somebody to do that. So she just sent another reminder today, I believe.
Yeah, well, yeah, in the chat there. Well, maybe there was an email too, but she definitely put it in the chat tonight. So
yeah, I haven't had any new learner or mentor registrations for ages and ages. So it might be because it's too cold.
Mm-hmm. Yeah.
Cold and wind chill and all that stuff doesn't really isn't conducive to observing or doing any astronomy, really.
And you know, at KP4 tonight, I think it's red.
Oh, for the aurora.
Yeah.
Oh, wow.
There was a big CME.
Yeah, but that's coming in 2 days.
Yeah.
Oh, okay.
Yeah, maybe we'll get some clear sky by then.
Not likely, according to the models, but
well, at least I'll be able to pick up the South American radio transmissions. That'll be fun. It'll blank out the regional stuff, and I'll be able to hear stuff from Bonaire and so on in the Caribbean. That'll be fun.
If you're not there. Anyway. So
tea time.
Tea time. Yeah.
We're trying to get our cat up here so we can show you, but she's refusing. She's let me just see here. Come on, come on up.
Here, kitty, kitty, kitty.
Come on. Here we go. So this is our relatively new cat.
Wow. She's huge.
Yeah.
She's like a Goliath.
I don't know if we told you about her before, but her name is Jupiter, and came to us like that. So yeah, or Jupy for short.
Rescue from.
I'm going to put her down so I don't get more scratches.
Yeah.
So.
She's wonderful.
So I always laugh in Jay's presentations, and here's the cat.
Now we get it.
I noticed Bryan did it tonight.
Yeah, that's right.
Well, it's kind of carryover from Gail when she used to do the I mean, it's just kind of an honor of her to always put a cat. And yeah, and I'm kicking myself because I do have a cat picture I didn't put in my presentation.
Yeah, but you don't realize how hard it is to get a new cat every month after you've done that program for 8 years.
Oh yeah, I bet.
And the internet is limited to the number of astronomically themed cats.
That was what Jay did for so long, that presentation.
Yeah. Has anybody ever used the meme, if the earth was flat, the cats would have pushed everything off it by now?
Oh God, that's so true.
Oh yeah, there's a couple of versions of that out on the internet. That would be a good one to throw in.
That's funny. Yeah, and they would have made whatever it is suffer. It would just be, it would be delaying, like just teasing it for a bit before it actually gets tossed off. So the way the cats
nobody would have a pair of matching earrings.
Yeah, that's true.
Oh man.
Yeah, a big problem with cats is who looks after them when you want to go traveling.
Yeah.
Yeah, we got that problem coming up. We're headed out to Quebec for a week at the end of March. So we got a neighbor coming over to check up on Jupy. So yeah. It's better than a dog for sure. Dogs are more popular.
I'm kind of hoping the world goes back to normal for us this year because we have somebody lined up who will move into the house for extended periods of time. But
wow,
big thing is shaping up for next year because we want to do a month or more in Australia.
Oh, nice. Oh, that'd be great.
Well, we go see an eclipse, and then when it's over, we'll jump in
we'll stay
4-wheel drive camper and just
sounds good. Sounds good.
I'm not turning green, am I?
Well, I've done it before, but without Judy. So.
Oh yeah.
Australia is easy to estimate expenses because everything is double. Twice as much as you would in Canadian dollars when you're down.
Wow.
Yeah. Sounds like Iceland.
Yeah, I think it's like that.
Yeah. Oh yeah, $20 hamburgers.
Telling me a story from Denmark. Was it Denmark?
I went out to it was in was Oslo, I guess.
Oh.
And we were going to scout an eclipse, and I got there a day early with one of the other guys. So I said, come on, let's go into town. We were staying at an airport hotel. Go into town. We'll have a couple of beers and I'll buy a dinner.
Mhm.
So we went in and we had a couple of beers. It was
St.
St. Patrick's Day. So it was pretty hopping place. And then we took the bus in from the airport, which is, it's about a 15-kilometer ride. Anyway, when it was all done, it was about 11 o'clock at night. Bus is still running, but what the hell, let's catch a cab. So we're taking a cab and I'm watching the meter and it rolls over 200 and I think, holy shit, that's in euros.
Holy crap.
So buying 2 beers, buying him dinner and the ride back cost me $450.
Holy crap.
Ow.
Man.
Yeah.
No wonder he takes it.
It's like, stop the car, let me out. I'll walk.
In the middle of a cold night in Norway.
Oh, good Lord. Holy doodle.
It was cold.
Yeah. Oh, man.
Anyway, I don't know how many times I have to tell a story before I get my money worth.
So Jay, mission for you. Your mission, should you choose to accept it, is please give us some warm weather. Whatever you have to do. I don't care if you have to,
Actually,
throw a sacrifice to the sky gods or I don't know what, but please.
This time next week, you'll be cursing the warm weather. Because the streets will be soupy. There'll be freezing rain and rain on top of the snow and all kinds of transit.
Well,
I'll take it.
Yeah, and we're all concerned about flooding too, right? Like if it warms up too quickly.
It looks like it's going to turn cold a week from tomorrow or Sunday. So but the temperatures, you saw the graph in Bryan's thing, temperatures hold at 0 day and night for about 3.5, 4 days in a row. And then they start in their up and down daily thing again. So both models are saying that, and they've been saying it for a couple of days now. So we're in for a soupy time, which means fog and no clear skies and everything else. So you'll get it, Darren, but you might not want everything you get.
Well, that's okay. It's my fault. I just bought a new big bino, so I guess it's my fault that I brought on.
Yeah, I think Gord's been waiting for some warmer weather too for a new scope, isn't he?
Yeah, I've had to take solace in reprocessing 10-year-old images, and they're working surprisingly well. I think I showed everybody that M31 image and the difference between the original processing and the latest one, but it just got all kinds of other stuff that's been sitting there for 20 years now. I think it goes back to about 2004. So just pull them out. Some of them, they can't have anything done with them, but
yeah.
There
you are.
Yeah, that's the reason, Jay, to keep all your old data. You can just keep on reinventing those images like crazy. New programs get to be more.
Yeah, about 6 months ago, I expanded from a 3 terabyte drive to a 6 terabyte drive. Now I'm looking at the price of 10 terabyte drives.
Maybe.
Well,
I have to buy 3 of them because I back up the 1 terabyte on 2 other drives.
They're not all bird pictures.
That's only 3 terabytes. With backup 9. Anyway.
Wow.
Memory's cheap. At least in a computer.
Nowadays, seems like it.
Computer memory is cheap. Real memory is.
I shouldn't talk because, Mike, how many gigabytes do you collect in one little run?
It's amazing how many you go through with video stuff for planets. Crazy amount.
You save all the video streams, or do you process them and then throw them away?
I've been saving them just because I figure I'm just going to hopefully get better at doing it. And I just can look at those again and reprocess them a bit. Much the same as you're doing with your images, Jay. You know, you have your old data. So just, you know, new programs come out, you learn some more tricks and you try different techniques with it.
If you run out of memory, I've got some spare 3 and 4 terabyte drives sitting in the basement I can't use.
Really? Are they like a USB 3s or what?
No.
No.
Some of them are. Some of them are only a year old.
I'll take them. I'll take all your USB 3s. Absolutely. I'm just looking at my supply and I think I'm really running short of them.
Well, you know what Anderson prices are like.
Yeah, absolutely. I love Anderson garage sales.
The guy said, I live in fear of after I die, my wife selling my equipment for what I told her it cost.
Secret's out now. Duh.
That's funny.
Well, gang, I'm going to call it a night. All the best to you guys.
Yeah.
All right.
I think I am too.
And, cheers to everybody, and we'll cross our fingers for some warm weather ASAP.
Yeah.
Okay. See you all next time.
Hey, guys.
Yeah, have a good evening. See you guys later. When I go, I think it's going to bring everything to a stop. So anybody need to stay at all, or is that it?
Oh, I think we're good.
Yeah, we're good. Okay. All right. Yeah. Have a good weekend, everyone. See you later. It was good seeing you.
Okay.
Good night.
Good night.
Bye.